Good morning from New York, and depending on what time zone you are, I know we have close to participants from almost like 25 countries and different time zones. So, good morning, good evening, good afternoon. I'm going to briefly introduce you the webinar and then the symposium, and then we'll get going with that. So starting with, first of all, before we move further, the backdrop of this symposium is on the Francis Key Bridge collapse. It has been a tragic event. 6 people died. Our thoughts and prayers for their families, and all the support they could get. But this collapse also has caused significant economic and other hardships to millions of people depending on the bridge for their livelihood, and we are dedicating this symposium to all the people affected by this tragedy. And we are hoping that this symposium will make some contribution to preventing any such tragedy in the future. Just to introduce the symposium, we have registration-wise, we have close to 750 people. Right now, I saw we had more than 400 people. The registration was more than almost 25 countries. We have expert speakers from different time zones: Denmark, Australia, China, USA. Just to emphasize, the symposium is in the webinar mode for all the attendees. Your microphone and video cameras are muted. That's normal, but you should be able to see the screen and hear the speakers talk. If you have a question, then please give a question in the QA box, and we'll try to entertain as many questions as possible. And some of the important questions we'll discuss in the panel discussion at the end. We also have a vote option in the Q&A, that if you like some question which is really important, you can upvote it, and that might get priority in asking the speakers. And besides this, whatever feedback you have, please put the feedback in the Q&A. It's very important. We are going to use your suggestion to develop a roadmap and proceeding of the symposium. For the PDH hour, a lot of you, this is very important. We are going to give the PDH hour. We'll be tracking your participation in this symposium to your Zoom registration. Scott, what happened? Scott?
No, I'm not sure. I'm resharing.
Yep. We given with the okay. So for the PDH hour, we'll track it automatically. You should be signed into this symposium, through the link that you received. And after the symposium, we'll calculate the PDH hours and let you know about it. We'll send you an email, and that should serve as proof of your PDH hour. This symposium is supported by USDOT Region 2. Center of the City College, and we appreciate the support of DOT and Center Director Kamga. We also appreciate the support of, or acknowledge the support of our co-sponsors, Med Section of ASC New York City and IBMS USA. In particular, from the Med Section, we have Gina Bundy, Douglas, and Dr. Castelli, who really help getting this symposium to you, and Dr. Alampalli from IBMS USA for providing critical help in all aspects of this symposium. On the back end, we have Dr. Jerry Hay, Mr. Scott Morris, and Okira Sanger for doing all the legwork in preparing this symposium. So thank you to them. It would not have been possible without their support. And finally, I'm very grateful to my co-chair, Dr. Sherif El-Tawil, for we have been doing collaborative research since 2014. This is the area of our passion that we are very interested, and he will be moderating Q&A at the end of this presentation. So with that, I will like to invite our Dean, Dr. Alexander Couzis, to say a few words about his vision about the School of Engineering at City College. So, Dr. Couzis.
Thank you, Anil. First of all, let me welcome all the attendees, all the participants. Can you guys hear me?
Yeah, hold on. Yep, go ahead.
Okay. Good morning, everyone. I'd like to welcome everybody to this online symposium that's been organized by Anil and Professor Anil Agrawal and Professor Kamga from the civil engineering at the City College of New York, Grove School of Engineering. I think this is an incredible opportunity to discuss the impacts and potentially come up with ideas on how to resolve impacts of infrastructure in this country, which we know is getting older and older. And when you look at the Francis Key Bridge collapse and its impact, that it's had obviously loss of life, direct impact in the area, the geographical area, but in the broader economic machine that we have here in the Northeast, how it has impacted things like manufacturing, the ability to bring in product, the ability to bring in raw materials, etc. So I think this is extremely opportune. I can't thank enough Anil and Professor Kamga for doing this, putting this offer together. I congratulate them both. I congratulate the organizing committee, and I wish all the participants a great symposium. I expect a lot of great ideas, which we will obviously also discuss at the Grove School of Engineering, because there's always opportunities for research and development and new potential intellectual property to get developed. So I'm extremely excited, and I welcome all of you. Anil, thank you for organizing this. Professor Kamga, same to you. Camille, as well. Very proud of having this symposium run through the Grove School of Engineering. And thank you again to all of you. Camille, Anil, the floor is yours.
Thank you. Thank you very much, Alex, and we appreciate your support. Next, I'd like to invite Dr. Camille Kamga, who is the Director of UTC at City College, and one of the co-chairs and sponsor of this symposium. So, Dr. Kamga.
Thank you, Anil, and good morning to all, and for working very hard with colleagues to organize and host this special event. On behalf of the University Transportation Research Center and our partners, I warmly welcome you all to this virtual symposium on the protection of bridge piers for large ship impacts. We are very pleased to see all of you joining us today, and are very excited of what we expect will be an exciting and productive discussion on the protection of bridge piers from large ship impacts. As mentioned by Professor Agrawal and Jean Couzis, we have gathered a great group of people who are in the forefront of this critical topic. And I know that you will not be deceived with the quality and depth of their presentation. Let me give you a brief background about our organization. The University Transportation Research Center is a federally funded university transportation center known as UTC at USDOT, representing the Federal Region 2 that comprises of New York, New Jersey, Puerto Rico, and the US Virgin Islands. UTRC, led by CUNY, is a consortium of 21 major universities in the region, with mandate to conduct research, education, and workforce development and technology transfer. The UTC program is administered by the Office of Research, Development, and Technology at the U.S. Department of Transportation. Last year, UTC was awarded $50 million in funding from the U.S. Department of Transportation University Transportation Center program for the Center for Social and Economic Mobility for People and Communities through Transportation, CIMPAC. CIMPAC lead the Region 2 UTC program. This grant will support research in creating informed decision-making tools, including the development of data-driven solutions for transportation agencies of all sizes. CIMPAC and its regional institution also work on inclusive, advanced technology to ensure that new technologies can be easily integrated into communities' daily lives. For more information about UTRC and CIMPAC, I will invite you to visit our website at utrc2.org. Before ending my remark today, I would like to acknowledge my colleague of the organizing committee for the great job that they did to plan and organize the symposium, and all the speakers for accepting to participate and share the ideas with us today. And a very special thanks to my colleague at the center, Jerry He, Okira Sangare, and Scott Morris, who have been the real force in coordinating and executing the program. With this, let me end my welcoming message with a wish for a lively exchange of ideas regarding bridge safety. Thank you, Anil.
Thank you.
I wish you all a stimulating and productive webinar.
Thank you. Thank you very much, Camille. Next, I'll like to invite Dr. Alampalli. He's the president of the IABMS USA, big supporter of Symposium. He will say a few words to introduce IABMS to this group.
Good day, everyone. Thank you, Anil. Good day, everyone. On behalf of the International Association for Bridge Maintenance and Safety, United States of America National Chapter, welcome to the symposium, which is promoting the safety of bridges to extreme events. And as Anil mentioned, I'm Sreenivas Alampalli. I'm a senior principal at Stantec. I'm the current president of the IABMS USA National Chapter. IABMS is founded. Can I move next slide? Okay, thank you. IABMS is founded in 1999 to bridge the gap between theory and practice. It was founded by Professor Dan Frangopal from Lehigh University and others, and it has been pretty active since then, doing biennial IABMS national international conferences as well as several workshops. It has a lot of national chapters, including USA National Chapter, which was founded about 4 years ago. To promote bridge maintenance, safety, and management in the United States, working with everyone, industry, academia owners, and everyone. I welcome all of you to participate when you get a chance. Here you have the website address here, or you can just Google for IABMS USA, and you will end up with the website. Membership is free, and I look forward to all of you actively participating. If you are interested, just contact me. Again, we have generally 3 events. We have some couple of webinars every year, and we have an annual meeting in Washington, D.C. in January during the TRB annual meeting. We also have biennial conference, as I mentioned before. The next conference in 2026 will be hosted in Orlando, Florida by Professor Cadbos and others from University of Florida there. So I welcome your participation. Again, the membership is free if any of you want to join. If interested in contributing to IABMS USA activities, please contact me. With that, this is the end my introduction. Again, thank you all for participating in a very important webinar. And Anil, Sherif, and Camille, thank you for organizing this. Again, I will chat with you all in the panel discussion in the end. Thank you.
Thank you. Thank you, Srini. Thank you, Dr. Alampalli. So, with this, before we start, with our keynote speaker, Dr. Pedersen, I just want to set some perspective on the, large SIP impact. So, Scott, can you share my presentation? Yep. So, so I just want to set some my perspective and the things we have been looking at, what really it means by large SIP impact. And actually, this is just a few pieces of information, but as we go through the symposium, you will hear from different speakers and you'll actually get a lot more detail on these things that I'm talking about. First of all, the collapse of the bridge. What really means a collapse of the bridge, like Francis K Bridge? Well, the bridge itself, the rebuilding cost is estimated around $1.5 billion. That's what I heard from people who are involved in the reconstruction. But if you look at the economic loss of this bridge over 5 years of rebuilding, there were 11.5 million vehicles passing every year. And if you look at the recent reports, they are like 2 to 4 hours. It takes 2 to 4 times longer to get where they are going. And if you estimate around every vehicle, in a day going and coming around, it spends 3 hours of extra time. And if you estimate the cost for the time, $50, which is the lower end, if you add it for 5 years, that cost itself is $8.63 billion. And then there are 4,900 trucks per day, hazmat trucks. They are subjected to 30-mile detour. That's an additional cost for that. In the region around Maryland, the increased accidents, reduced mobility on other highways because of the collapse of the bridge. This is from the actual traffic data that traffic crashes increased by almost 29% on alternative highways since the collapse. There's increased pollution, air pollution, wasted fuel, other environmental impacts, loss of use of port facilities, and loss to local businesses. If we add all these costs, probably the estimated loss because of this bridge, the actual reconstruction cost is very small fraction of that, $1.5 billion. Overall economic cost to the region in 5 years is probably more than $20 or $30 billion. So this is what it means when we talk about a critical asset, that we need to protect this asset by considering a risk that may be, almost may seem improbable. And we have seen from other lessons, other collapses that happened in last, couple of decades that, although the risk is, very improbable, but looking at the amount of impact, the damage, that we must take extreme measures to make sure these assets are protected. Now, when we talk about this, the large ships, well, ships have been growing. So I found this very interesting chart that this is MB Dali here, which is around 300 meters. This is not the largest ship. The largest ship is actually 400 meters. And if you, for comparison, you see the Empire State Building, and these are like almost to the size of the Empire State Building. Some of the guidelines that we have, this is a 1970 era guideline. This is the height, and US typical field, football field, you can see the dimension. So you can see the scale that what we are looking at. In terms of, the size of ships, they are defined by the cargo capacity. And the cargo capacity are essentially TEUs, which is equivalent 20-foot containers that a ship can carry. So 1970s, we had a very small TEU. Dali had a capacity of almost like 10,000 containers. The largest ship that we have right now, which is, I think, one of the, Alina, there are a number of ships here, which are almost the container capacity is around 25,000 TUs. So these are massive ships. But also if we look at another data that how the loading of these ships are increasing, then we can see the growth of the ship from 1960s all the way here. And we are here. So Dali had a DWT, what we call is a deadweight tonnage. It's almost close to 116,000 ton. And the one of the heaviest ships that we have now, the deadweight tonnage is, around more than 240,000 ton, more than double of the Dali. But also, for impact engineering, when we think about the impact, we have to consider something called displacement weight, which includes the weight of the boat itself. So if you include the weight of the boat itself for Dali, the weight will be actually not DWT, which is 116,000 ton, but it will go to close to 150,000 ton. And one of the largest ships, their weight is around 10% is the self weight, so they will go around like at 280 to 290,000 tons. So these are massive ships, and what actually these massive ships means in terms of guidelines. So I found this, and Professor Pedersen will talk in detail about his research. But I was reading his paper almost close to a month ago when I realized what really this large ships means. So this is the DWT and this is the crashing force. And this is our ASTO guideline that you see the blue curve and it's uniformly increasing. And this is, there, by other methods that you calculate the impact forces. And you can see that after southern DWT, the impact force increases so much, it's way higher than what we have from the ASTO. And if you also look at the ship length has a significant impact on the impact forces. So what guidelines we have right now in ASTO, which was essentially based on, what they triggered after Sunshine Bridge collapse in Florida, we need to look at those guidelines to see what exactly we are doing. But the bigger question is, do we really have to design the bridge for large ship impact? Does the bridge have to take all the, impact forces? Well, similar analogy is when we do the blast protection of buildings, that when you go in front of buildings, you see these bollards. And these bollards are basically there so that a vehicle cannot get close enough to the building so that the shock effects don't go and affect the building so much. If we go to the same thing, then this is a problem of risk management, that we do whatever we can do to prevent the ships from impacting bridge piers. We could use rock islands, pedestals, platforms, barriers, dolphins, whatever works. Impact resistance of the pier, of course, they should be designed for impact, but that should be the last line of defense. We need to do continuous assessment based on the ship traffic and AI data, and Zoli from HNTB is going to talk a lot about his insights into this one. We need to design the system for guaranteed performance, and the computation technology allows us, just like we do for the barriers, bridge barriers that you see on the highways, that they are crash tested, then they are verified through simulation. We could do the same. We could design the system so that tragedy like Maryland Bridge collapse doesn't happen. And most important, we should not be planning for these critical bridges for a couple of years. We should be planning for the expected life of the bridge, that we do one-time investment, but then some upgrades, and we can keep on making sure the bridge is safe from future large ship impact, which we see clearly that it's a lot different than what we had in our guideline or what we have been doing right now. So, but there's another interesting aspect that really we don't know, and we have not thought about it what to do, is when you have a ship directly under the bridge and it goes and hits the superstructure, then we don't have those options like protect the pier. We have very few options. And this is one incident you see on the right side of the slide, that the ship came and just ran into the superstructure, took the bridge out. I remember, many years ago, around 2000, there was an incident in the East River Bridge that one of the ships had some equipment not secured. It had hit part of the bridge, a major bridge. Unfortunately, nothing happened. But this is another problem of large ship impacts on the bridges that we probably need to think about. So these are some of our thoughts, but I think we are going to hear a lot more from our experts on this topic, and we are going to learn a lot. And your feedback is very important because based on your feedback, we have a lot of people in this room, and we want to get all kind of feedbacks, so we can develop a roadmap based on the symposium that where we could go in addressing this problem. So with this, I will like to invite our keynote speaker, Dr. Pedersen. Thank you.
Thank you.
So let me introduce Dr. Pedersen, who is currently Professor Emeritus at the Technical University of Denmark. Dr. Pedersen has the whole lifetime of work in this area on ship impacts or ship-to-ship collisions, wave-induced loads on ships, offshore structures, ship collisions, grounding, and risk analysis related to maritime activities. He has, if you look at the literature, his work goes back to 1973, and he has done most of the pioneer work in this area, and I'm very grateful to him that he agreed to address the symposium and give us a presentation on his perspective, but also like where we are going in terms of large ship impacts. So with that, I will like to invite Dr. Pedersen, and Scott, if you could share Dr. Pedersen's PowerPoint, and please give him the access.
Thank you, Professor Agrawal, for inviting me to give this introduction to some elements which we have for bridge design against ship collisions. Let me see if I can change. No, this doesn't work.
Scott, have you given it the control?
I don't have control here.
Scott? Do you have the control now?
Oh,
Yeah.
now it came. Now it came. Okay. Well, let me start by saying a little bit about what I'm going to talk about here. First of all, I'll try to give you a little bit of my background for giving this talk. Then I'll talk about criteria for risk acceptance. What should we strive at? Ship collision probability analysis, and then consequences. And these consequences I'm going to talk about will really be restricted to the ship impact forces. So that is what I want to talk about. My background is, as was told, I'm a professor in naval architecture at the Department of Naval Architecture in the Technical University of Denmark. And my fields are really mechanics and naval architecture. But so I've also a little bit of practical experience, and that's what I'm going to talk a little bit about here. I was advisor for an offshore company on ship collisions against some production platforms in the North Sea. And with this background, the bridge owners in Denmark, that's the government really, asked me to be advisor to them on some ship collision issues related to some bridges we were going to build in Denmark. So that started in 1988 with this Great Belt Bridge, which we have here. This Great Belt, that's really the entrance from the North Sea and the Atlantic to the Baltic Sea. And that is all the ships which goes to harbors in the eastern parts of Sweden, in Finland, to the Russian harbors in St. Petersburg and Kaliningrad, to the Baltic states, to Poland, and the northern parts of Germany. They have to go through here. So we ended up with a bridge with a very large span. At one point of time, it was the longest span in the world for a suspension bridge. And of course, we had to secure it by artificial islands around some of the most exposed piers, as you can see here. After this bridge, we worked on the ship collisions against a bridge between Denmark and Sweden. That's Copenhagen here and Malmö over here. And that ended up with this bridge here. There's not that much traffic here because it's more shallow water. Finally, I was working on as an advisor also on a bridge to Germany, from Denmark and to Germany here. And here, of course, we have all the traffic from the Great Belt and also from the Kieler Canal. So again, we had lots of ship traffic, and we have relatively large water depths all over these about 20 kilometers. And that made it quite expensive to secure this bridge against ship collisions. So the government, that was one of the reasons why the government decided that we should have a tunnel instead. And this tunnel, so now the ship collision is really transferred to problems or ship collisions against barges or excavation vessels and throwing out tunnel elements. And this is going on right now, but still, this is also a challenge on this heavily trafficked area. I've also been working on some bridges in Norway as a technical advisor on ship collisions. And in Norway, in the western part of Norway, the Norwegian government wants to have bridges over some of these very beautiful fjords they have up there. And I'm especially involved here with the Bjørnefjorden, where we were looking at different concepts. These fjords, they are all about 5 kilometers wide, and the depth goes all the way up to about 1 kilometer. So the only way we can support a bridge is by buoyancy. So we were looking here at the risk associated with a floating suspension bridge, as the one you can see here. These pylons, they have sufficient buoyancy to carry the bridge and also have tension in these tendons which go down to the bottom to stabilize it. We were looking at submerged floating tunnels, either stabilized by floaters at the surface or by wires to the bottom. In this case here, of course, you don't have any problem with ship collisions because these tunnels will be situated about 25-30 meters below the sea surface, just to avoid a wave action. And of course, we don't have ships with a draft more than 20 meters. And finally, this one here, this is a bridge on floaters. So all the piers here are on floaters. This here, of course, you have substantial ship risk problems. This one is actually under construction now. So that was a little bit about my practical background. So now I'll go to more technical matters. First, criteria for risk acceptance. I think it's good to hinge the discussion up on what is risk. We know that risk is a combination. The risk R is a combination of the probability, PI, of an event and its consequences. Normally, when we talk about risk and risk acceptance criteria, we have to sum all the different types of risk. And this could, of course, be earthquakes, fire, or airplanes crashing into pylons, but above all, of course, ship collisions. And I'm going to talk here about the probability of accidents and consequence, give some more information on that. Of course, you have to do risk analysis during the installation, but I'm only going to talk about operational risk. We have to look at the risk for the users of the bridge. The risk for the user of a bridge should probably not be much higher than the risk of driving on an ordinary highway. So that is, of course, one type of criteria you can start off with. There's a financial risk for the owners. That's obvious. We also have risk for third parties which do not draw advantage from the bridge. If you look at, say, the Danish bridges I showed you, they are all over international waters. And then the the IMO, the International Maritime Organization, it's a UN organization, they have requirements that it should not be more difficult for the ships to pass under the bridge than it was to pass the bridge line before it was constructed. So that is something to take into account. And then there's risk as a result of the socioeconomic impact. And that was very well described for this, for the Baltimore Bridge by Professor Agrawal. So this is normally a huge impact, really, a large economic loss. And of course, we have to look at environmental risk. So all this leads up to some risk acceptance criteria. And it's obvious that a primary measure of performance for such a bridge will be to ensure that the occurrence of large accidents with fatalities, that a bridge falls down, for instance, and lengthy interruptions is low enough to be acceptable to users, the public, and the relevant authorities. But we cannot ask for zero risk. We must at the same time allow an economic construction and operation of the link. So that is this balance which we have to do. Of course, the risk level is very small, which we shall accept. So therefore, the likelihood of future rare events, such as ship collisions, we cannot predict this or extrapolate this from similar events elsewhere. That's simply not possible. So the best we can do is to try to establish models, even if these are difficult to verify. And of course, because of the small number of accidents. So we cannot measure the risk particularly well, but we can decide what the level of risk should be, and then use a model to verify that these selected criteria are met. I really think that the risk level should be hinged to the acceptance list should be hinged to the model you're using to verify it. Okay, so now I'm going to talk a little bit about this ship collision probability analysis. That was the PI in the formula I showed you from one of the previous slides. We know that the ship bridge collisions normally happens due to human errors and due to technical errors. Here I have tried to use a model, well, I'll try to describe a model where we divide the accident categories in 4 different categories. And the 2 first, they are really related to human errors. The idea is that you try to calculate the collision due to human error based on an estimate of the number NA of collisions in case of blind navigation and no aversive maneuvers. Just imagine that you have ships which approach the bridge and on the ordinary track, and so it's on track. But suddenly there's nobody on the bridge. They are drunk or they're sleeping or gone away for some private errand. In that case, we will have a large number of collisions, NA, which is of course proportional to the number of ships. And of course, it is also dependent on a geometric probability. What is the probability that you hit a pier? Because a large part of these vessels will go through the opening of the bridge. So this is without navigators. So the effect of navigators has to be included here, and that's done by this causation factor PC, which is the probability of a collision if the ship is on a collision course. This idea here was developed by Dr. Fuji in Japan. He was studying accidents in the Bay of Tokyo, and he really laid the foundations for much of this here. Then there are technical errors, of course, as we saw with Ali in the recent disaster, where you have loss of propulsion, a blackout, or loss of control, a steering gear failure. And finally, the last one is evasive maneuvers in the neighborhood of a bridge. I'll give a little bit more detail about these 4 categories in the following. Category 1, that is ships which follow the main route. So here you can see, here we have a bridge line, and we have a 2-way traffic situation. And let's consider ships which are coming in here from the south. Ideally, they should all be here right in the middle of the navigational route. So it should be right here. But of course, due to wind and waves and general navigation uncertainties, then of course you will have a certain distribution here of vessels on this line here. And we can call this distribution f of z. And you can see that part of this probability area we have here, they'll collide with this pylon here if they don't make any change in their course. So this is the NA, that is the integral of this function fz over the width of this pylon and multiplied with the number of ships. So that was the NA we had before, and now we can multiply that with this causation factor, which of course depends on a lot of things, and you can influence that. For instance, having a pilot on board, and you can have a vessel traffic system or guard vessels and have good markings here. So this will all help you to reduce this PC here. I have a summation here because we have to do this calculation for a number of different ships, because in order to determine the consequence of such an impact, then of course we need to know what's the size of the vessel. Is it, and then of course we can have a class which is ships between 110 and 125 meters long. And we also want to know, do they have ice strengthening? Because then you have higher forces. And we would like to know, is it in fully loaded condition or is it in a ballast condition, in order to evaluate the consequences. And that's why we have to have a number of different ship classes. But of course, the total number will give you this the collision probability for this pier. How do we get this FZ then? How do we get this distribution? Here we are very lucky that we have got what we call AIS, automatic identification systems. We can simply, all ships above 300 gross tonnage, they are entitled to, they have to have a transponder which tells you a lot about the ship, which ship it is, what's the loading condition, speed and direction, all that. So with that, we can get the tracks of the ships. This is this area where the Fehmarn Belt, where we now have a ferry traffic. So if we want to have a bridge here, then of course we can see what is the distribution of vessels here. And you can get these distributions from this AIS. And of course, such a distribution, you could use it directly as a histogram, but you could also, of course, try to fit a curve and get a log normal distribution or a Gaussian distribution or something like that. So that is, and of course, we can also get the present number of ships per time unit passing this line here. So this was category 1. Category 2, then it will be ships which fail to change course at a bend in the seaway. Let's have a look at the same figure as we saw before. We have now we'll now consider ships which come from the north. And there is a bend in this seaway, as you can see here. But some of the ships may not observe this, may not do this bend. And if they do that, then of course you can see there's much larger probability area here, which can collide with the pylon than what we had before. And you can see it also over here. We'll have a much larger geometric probability. So this N ship times Fz, that is a much larger value here. And of course, it's the same PC. But then we have to multiply it with the probability that they do not make this bend. And that's hopefully a small number. This P naught, that must of course also depend on the distance between the bend and the ship and the bridge. Sorry, this distance D here. If this is large, of course, the navigators has more time to discover that they are on a wrong course. How do we get this P naught then? Again, we can try to use this AIS. Here's an illustration of a ship which passes a bend. So we have here, that's the route, and that's where nearly all the ships go. But there's one here which goes with unchanged course and speed until it's nearly ground before they find out that it's on a wrong track and then come back again. By studying AIS tracks, we can get a lot of information about this P naught as a function of this distance D. When we were working with the consultants on this Great Belt Bridge, we wanted something to test this, these models, category 1 and category 2. First, we had only category 1. And then we were looking at groundings in the area. And then we saw there was a cluster of groundings here. And we were a little bit surprised. And then we noticed that ships which come from the north, which did not make this bend here, they will end up over here. Similar, we had a lot of groundings up here, and that would be ships which came up from the south. And this cluster here, they are close to the shipping lane. So, and these are some shoals, and the grounding on these shoals, we say that was category 1, this is category 2, and this is category 2. So we could use this to adjust our model. Of course, this shows that you could try to make bends in the seaway such that those who do not make this bend don't end up against the bridge, but ground before that or go through some of the openings against in the bridge. That's something you have to monitor the shipping lanes going up to the bridge to reduce the danger. Category 3, that was a problem related to the loss of propulsion and steering gear failure. Ships, they have a blackout, and it happens. Well, some published figures for that. That is this 1.5 times 10 to the -4 failure power. It corresponds to once or twice a year, something like that. That's exactly what we saw with Dali against the Baltimore Bridge. Of course, there is a chance that you can repair, that you get the engine started again. And one used formula for that is Weibull distribution given here. And you can see a graphical representation here. And you can see that there's about a 50% chance that you get the engine started within, say, 15, 20 minutes, something like that. And then the ship will probably be on the same course and just slow down a little bit, not very much actually. So that is one way, of course, and the rudder failure that's given by this number here. But if it takes longer time before you can have the engine started up again, or you cannot, for instance, set out anchors to stop the bridge, stop the vessel, then the ship will start drifting. And then the drifting, a ship will normally drift sideways. And of course, the direction and the speed, that would depend on the current in the area, about the wind in the area and all that. But that really you have to take into account. Steering gear failure, here you have to be aware that it happens sometimes that the rudder locks in an extreme position. And then, of course, you can have collision with which Piers with relatively high velocity, because then you cannot stop a ship within a short distance. The final category for collisions, that is evasive maneuvers near the bridge. If the bridge opening is a little bit narrow, then there are ships with large ships meet, then they may be scared and try to do evasive maneuvers, and that may end up with contact with the piers sideways. You can get an idea about that possibility, by looking at these safety zone, or say comfort zones. Each ship has such a comfort zone or safety zone around it. So if another ship is inside this comfort zone, then they'll quite often try to make evasive maneuvers. These comfort zones, that has also been studied by AIS to see what's the size of them. For open water navigation, it's something like this. It's a proportion to the length of the vessel. When you know the length distribution of the vessels and the traffic, then of course you can make a simulation and see how many close encounters do you have per year as a function of the span width here in kilometers. So if you're down here, then the number of evasive maneuvers will be quite small, and then it may be something you can neglect. But if you have an existing bridge, it may, with too narrow opening, that may be something you have to think of. Okay, so now I've given you some elements in the ship collision probability analysis. So the next thing will then be, if we then have these ship collisions, what are the consequences of these collisions? There are many ways in which the ship can collide with a bridge. Here is depicted a sideway collision, which can be due to, say, drifting, or it can be due to maneuvers in the vicinity very close to the bridge. So we need formulas, we need expressions for sideway collision forces. And we also saw in Professor Agrawal's presentation that deck house collisions, and that is something where we have a lot of spectacular collisions, where the deck house or a container stack collides with the bridge girder near the abutments. But here I'll mainly focus on bow collisions. You have a ship which here collides with this is a pylon, but we'll look at, say, collapse and the forces which such a ship bow can exert against some rigid wall. Exactly, that's what we're trying to do. A ship bow is really a complicated structure. And this is an ordinary vessel which without ice strengthening. And you can see, for instance, the bulbous bow here. You have lots of close stiffness here. And when you have such a complicated structure, you always think, oh, we can use nonlinear finite elements to make the analysis. And that's, of course, true, because here what we have is large geometric deflections. We have large material strains. We may have fracture. It's a welded structure, and there may be some defects which cause fracture. And we have contact problems. You have lots of contact problems because this bow can be compressed nearly all the way up to this collision bulkhead here. And then I simply, because of these complications, and because we want to make a lot of generic ship collisions in order to get some mean values, then I prefer to use simplified methods because we don't even know what will be the future striking vessel against our bridge. So simplified methods. Simplified methods, quite often, they are based on this, what some of us have, or most of us have learned at school, the upper bound theorem of plasticity. It goes like this. You take the bow structure and make a cut at each frame, for instance, and then you look at what kind of strong elements against crushing do we have here. Well, we have L sections like this. We have T sections like here, and we can have some X sections or cruciforms as one down here. For each of these sections, you can then calculate what is the crushing force. And that is, we assume a certain kinematically allowable displacement function or collapse function. And then we calculate the energy which goes into bending and stretching of the material. And we do that for these sections. And from that, we can then get the forces by looking at the distance divided, the energy divided by distance. And that has been done and also made even easier to use by two well-known authors in this area. Jan Hamdahl, in his PhD thesis, he presented this formula here. And here you can see it depends on the number of X sections and number of T sections, etc. Sigma naught, that is the flow stress. That's the mean between the yield stress and the ultimate stress. And the Young and Court will have a similar formula here. The question is then, how good are these formulas? We can have a look here. There are many examples in the literature of where they have tried to make small models and compare with these. We tried to make these formulas. We tried to make some a little bit larger scale tests here. So this is the real ship, which we then divided by 5 and got these specimens here. They are about 1 meter high here. and we had 3 different internal stiffness system. And here you can see the quasi-statically crossed bows. And you can see it's very short wavelengths. We have a little fracture. There's a little bit of fracture here. That's good because we do not take into account fracture in these models here. And yeah, the next slide shows the physical test results. And we can see these 2 Amdahl and Young and Caldwell approximations here. And you can see they more or less bracket these test results. So we actually use the mean value for these 2 procedures. You could say, why don't we use full-scale testing? Because that's the real test. And there are many ship-ship collisions, for instance. But in ship-ship collision, it is such that the bow is normally the very strong part. So the striking bow in a ship in the stock vessel will normally always penetrate the side shell and the stock vessel. So we don't get much information about the bow strength from such collisions. And of course, you could take an old ship which are on the way to its scrapyard and then run it, instrument it and run it into some fixed object. But that would be expensive. I've not seen anybody who's willing to sponsor that. So, but I was fortunate enough to be involved with an accident where a ship came into an harbor and then suddenly they had a blackout, like the Dali. And so the people, the navigators on the bridge of the vessel, they couldn't do anything except notice what happened. And they noticed that the speed of impact against this caisson or breakwater, it was 5 knots. This displacement of ships was a little less than 100 tons. And I was looking at this bow, and then I could calculate that the average crushing force is 65 meganewtons. That's what I found. And the caisson had a mass of 16,000 tons, and that was displaced a little less than 1 meter, 80 centimeters. And if I assume a certain realistic coefficient of friction between the bottom of the caisson and the sea and the ocean bottom, then these forces, dynamic calculations show that this is very good. This corresponds very well together. This is not a good proof, but at least it does not violate our belief. Okay, so we use these 6 ships to develop a design formula. So we took the drawings of 6 ships, 3 bulk carriers, as you can see here, 1 tanker, and 2 container vessels. And for these ships with different loading conditions and different speeds, we did calculations of the bow collision forces. And you can see the result here. This is the Amdahl curve, and this is the Young and Caldwell. And you can also see we try to make separate predictions for the bulbous bow, because we have a step here. We would be nice to know what is the bulbous bow forces. So we did that for all these 6 ships for different speeds. And based on these results, then we took, of course, the maximum forces here, and then tried to make an empirical formula for maximum bow crossing forces, which can be used by bridge builders. And we used as a free parameter the kinetic energy mv squared. So we have the mass included and the velocity, and we also included the length between the perpendiculars. And this length is a very really determines the scantlings of a ship hull, because the wave-induced loads depends very much on this LPP. So length is better than deadweight tonnage, according to my opinion. This formula which we derived here, that has the same format as the present Eurocode. So let's try to compare this with what we have in the existing codes. We did a similar calculation in 1993 for 6 different vessels in connection with the Great Belt. They were all strengthened according to the DNV Baltic Ice Class. And we did that because the entrance to the Baltic Sea in wintertime, there you have to have ice class. So a good proportion of all the ships going through the Great Belt had ice class. And to be conservative, we assumed, now we had this calculation, we assumed all ships had this ice class. So that's of course a conservative, that's a conservative idea. Identical expressions were then adopted by YAPSE SED04. That's this green book many of you probably know, which was published by Ole Damgaard Larsen. And of course also, and it was also adopted by Eurocode for a speed of 5 meters per second. Unfortunately, they did not mention in the Eurocode that this was developed for ice class vessels. And another recommendation is, of course, the US guide ASTO, which has this shape here. And this is depends on the deadweight tonnage and does not depend on the loading condition. And of course, you know, there's a quite a large difference between a loaded bulk carrier and a one in ballast, more than a factor of 5. Here you can see what we have, what these three different predictions will give. This is one which I have presented here for non-ice class vessels. This is for ice class vessels. This is of course much higher, but of course you also, when you start breaking ice, meter thick ice with a bow, you need a lot of stiffening, internal stiffness, and you need really more heavy plating. And this is the ASTO. And of course, for ships up to about this size here, then you will have, it's not far off, but for larger ships, the distance is much greater. We can have a look at a medium-sized container vessel. This is this Emma Maersk, which was, well, it started regular service in 1998. I was very much involved with the construction with that, so I know it very well. Here, this can take 15,500 tow, and it was the largest of these ships at that time. It's about 400 meters long. And these are partially loaded. So fully loaded, the displacement will be 220,000 tons. So 120,000 tons, that's a very light ship. And you can see that in all cases here, for no matter what the speed is, you have very low predictions by the ASTO. We also want to know what is the pressure, local pressure. When you design a pier, then the local pressure is important, of course. You do not want local damage before you have overall damage. And here we tried to look at these bows for these 6 different ships which we had, and then look at what is the force divided by the outer area of the bulbous bow at that penetration. And you can see, so this is some average pressure, you could say, as a function of this imprint, AW, that is the cross-sectional, the outer bulb cross-sectional area. And you can see there's lots of scatter. We have here a mean curve, which is given by this. This is the same shape we chose as we have ice pressure, and we have, of course, also more or less the same scatter as we have in ice pressure. What I've been talking about now is what you can do when you design a bridge, and of course we should, know that a bridge will have a lifetime of 50 to 100 years, and a lot of things happens with the number of ships, the size of the ships, and the structure of the ships, and we will have a lot of new navigational equipment. And hopefully we will also get better prediction methods. And so for this reason, we should, at a regular intervals, say every 10 years, redo these calculations to see that we live up to the requirements. These set up by authorities or whatever we have. Okay, I'll come to the conclusions for my talk. The collision frequency model is depends on empirical and uncertain factors. such as the lateral distribution, FFZ, and the causation factor, PC, the probability of meeting a course change, P0, etc. With AIS, we have got a lot of new information about these quantities, but we should really try to get further data to improve our predictions. That's very important. I have not talked about it here in this talk due to time limitations, but last-minute actions of the colliding ships should be investigated. When a ship, well, we know from ship collisions, if we look at say damage report damage reports which are made after two ships have collided, then it's seen that the colliding vessel, that is striking vessel, has a speed at the moment of impact, which is something between 0, a little above 0, of course, and up to full speed. And it's more or less equally distributed. If the same happens here, the navigator is so close to the pier that he cannot really avoid an accident, but he'll do things, whatever he can, to diminish the speed, to change the course and things like that. And if you can mitigate the damage by that, then of course you should do that. You should try to take that into account. This is today we do this by some Heinrich factor, but this is very coarse. Here we really need to do more research. The new expression for bow impact forces show that the YAPS and Euroco recommended bow forces for ships with ice strength, and that gives too high values for those for ships which are not ice strengthened. So we should really keep track of which ship is what is the proportion of ice strengthened ships and non-ice strengthened ships. The crossing forces recommended by ASH to underestimate the crossing forces for larger ships. Also, I think that a new ASTRO expression should be dependent on the loading conditions. And further work, we need further work for, further work for step piers, partial impacts, and of course, dynamic simulations of the impact. In this force, the new expression, we took into account damage, the speed using this Cooper-Simons relation, but we should do it in connection with the peer response, of course. Okay, I have to thank this presentation is primarily based on 2 papers, and I really want to acknowledge the very heavy contributions from my co-authors, Sverre Valsgaard, Dan Olsen, and Søren Spangenberg, and Yin Chen and Ling Su. They have done a lot of work in this. Thank you very much.
Dr. Pedersen, thank you very much. My name is Sherif El-Tawil. I'm the co-organizer for this symposium, and it is my privilege to handle the questions that have been produced. Thank you very much. It's a very interesting presentation, and I see a ton of questions. So we're going to go for the number of questions we can handle, and then just go from there. So first question is from an anonymous attendee. It says, for floating tunnel below depth of the ship draft, was the risk of terrorism considered for exploding or bombing a ship when it's above the tunnel? This pertains to the very first part of your presentation.
This is a very good question. We do, in those cases where I've been involved, we have avoided to introduce risk for terrorism. It goes for the bridges as well as tunnel, because of course you can try to make a layout of the tunnel and the bridges such that it's difficult to hide anything. But we don't really think that we can make any estimates of this. It depends on things which are outside engineers, the engineering profession, like politics and things like that. But it is a risk which, well, but it's not taken care of in what I've been involved with. But we have discussed it, and we decided that we can't do anything.
Okay. The second question is from Marky Rowland, and it says, when you have ships going under a bridge, why can can't they go normal to the bridge rather than at an angle? At the time you were discussing the path.
They should go. They should go, of course, to use the bridge opening. You should not go normal to the bridge to avoid to this. But of course, it is whether you can organize. We tried to reorganize, for instance, for the Great Belt, we reorganized the shipping lane such that it was nearly normal, or very close to normal. And then, as I said, so when we had to introduce some bends in the seaway, and then we tried to move these bends as far away as possible from the bridge, and also organize them such that many of them would go, those who did not make this bend would go through the bridge or ground before they came to the bridge. But it's very important to do this this type of layout of the shipping lanes.
We have a question from Jason Stith. It says the probability function f of z, spatial distribution for AASHTO uses the length overall as the standard deviation for the normal distribution function. This seems really conservative. Since you have looked at a lot of AIS data, do you have a recommendation for more accurate spatial distributions that AASHTO should consider?
Here the problem really is that before you build a bridge, you have a certain distribution f of z. After you build a bridge, you'll have a new distribution, but you don't know that before you have built the bridge. I showed you those distributions which we had for Fehmarn Belt. I have distribution for others also, but the Fehmarn Belt, you saw these distributions, but they are without the bridge. So this is what you can get when you build a bridge. Then of course AIS can give you a new distribution, and I would say also this with the lengths, all these distributions. When we made the Great Belt Bridge, we did not have AIS. The only thing we could have a look at that was radar. AIS was not introduced at that time, but now we have all this information, and then now you can get much better information.
Thank you. So it seems, Jason, this question is also relevant, I think, to other presenters. So I'm going to keep it, and I think we'll ask other presenters as well. And maybe it would come up in the panel discussion too. Moving right along, so Abdel Denho, his question is, this approach takes the crushing of the current ship types or design. Does it take into consideration any changes in future ship designs and shapes? Like, how do you predict the future in terms of the impact projections that you're going to get?
That's another good question. You can, what we do normally is that when we look at what is the present traffic, and then we make projections based on interviews of, for instance, in Norwegian fjords with the industries inside, who they expect in the future and all that. But we can also follow what's happening with the vessels, with the ships. When we do recalculations for the Great Belt, for instance, then we can see there's a trend for the vessels that they we get fewer vessels, actually, a little bit fewer vessels. But on the other hand, they get larger and larger. So what we get is larger vessels. And of course, there'll be a limit to that. But at the moment, we have these 23,000 ton tow container vessels, and it'll be a jump if we get larger than that, because then the cranes cannot accommodate it and all that. But you have to do this to look at that. When we built the Great Belt, we thought that the largest vessel against the Great Belt Bridge would be a partially loaded large tanker, partially loaded due to draft restrictions. And but then 5 years later, we got these new generational container ships, this Maersk, the one which I showed you, partially loaded. And that, of course, gives much higher, quite higher collision forces than these tankers we used previously. So that is something, then you have to redo all your calculations with this new number here, with new ship types. But that's what a ship will live about 20 years. So we can only predict about 20 years. We know the ships which we build today, they'll be around for another 20 years. So it's not something which happens overnight.
Well, this is a societal issue, though, because what you're saying is, okay, we know that the ships are going to grow. We know that the risk is going to get higher. And yet it's very difficult to take action on something like this. So for example, it could culminate in a situation like what happened in Baltimore. And I know you may not have an answer to this because it entails the resources we have as a community, but I'm curious if you have an opinion.
Yeah, it's that's the reason how you protect. Of course, you can have restrictions. You can put in, I say, speed restriction. Now, Baltimore is a good case because there it is a national waters, so you can put all the restrictions you want. You can also say put an upper limit to the ships which must pass there. So of course it has some economic consequences. But you could have, for instance, speed restrictions, and you can have guard vessels. All these different types of things you can do to reduce the problem. Of course, you have pilots there, but guard vessels could also, if you had guard vessels in the case of Baltimore, you may have had a chance to redirect it such that it did not collide with the pier. So you have to look at all these different concepts which you can introduce.
Okay, great. So moving right along from an anonymous attendee, for the geotechnical analysis and design uncertainties question, how does geotechnical, for example, subsurface characterization, how is it modeled in your vessel impact analysis for an existing bridge? Do you require site-specific subsurface investigation and lab testing for any proposed mitigation objectives, or do you rely on existing geotechnical data? So for the foundation system. Yeah.
This is really not my area. As I told you, I'm a mechanical engineer and naval architect.
Okay.
But
No,
no, that I will not answer that. Because I know there's made such many, really a lot of geotechnical inspection when you build a bridge. But I don't know. I cannot answer that.
Understood. So Ishwarya Srikanth, the question is, can you please elaborate more on the consideration of the loading condition in the AASHTO provision for impact force calculation? Shouldn't we design for the worst case scenario, a fully loaded condition? And the loading condition is also accounted for under the vessel condition energy computations. And I also would like to ask you this question following up on this is, why is the force equation dependent only on the deadweight tonnage and not the full weight of the ship? So
yeah, I really propose that you should look at make an analysis when you build a bridge or when you evaluate a bridge of what is the loading condition of the vessels which go. For instance, a tanker or a bulk carrier, their lightweight is something only 15%. The mass of the lightweight structure is only about 15% of the fully loaded vessel. And you should take that into account. For most of these vessels, bulk carriers, for instance, they're either fully loaded or in ballast. And of course, you should take that into account. You should not always take the worst. You should take into account what is the most realistic. So that, I think, is the way to do it. And you should not, I don't think it's a good idea just to use the dead weight, as I told you, because the dead weight for the what should I say, a passenger vessel, for instance, or a cruise line, that's of course a different measure from a dead weight from a tanker. So that does not. Then you have to have some translation tables for different ship types. I think it's much better to use the length of the vessel as a measure. But like with the mass of the vessel, you should also take into account how large a proportion of the vessel of the ships will have ice strengthening, and which proportion will not have ice strengthening, because that makes a lot of difference, as we saw on the collision forces. You should make it as realistic as you can.
So there's a related question from an anonymous attendee, which is, and this is our last question. Again, there's a lot of interest in this presentation. There's so many questions, so I'm just trying to choose between them. But is there, speaking of how realistic something is there a maximum ship size that is realistic for design and operation? And it's kind of related to previous questions and an unknown future as well. So do you have any last thoughts about this?
Yeah, of course, as I've mentioned, those container vessels which we are building now, they're nearly all the same size, 23, 24,000 ton at a tow contain 20-foot containers. So we will have them for a long time. I don't foresee a jump, as I told you before, in this size range. But then on the other hand, the idea is that we may not have to design against these very, very large vessels, and especially if there come 1 or 2 new vessels which are larger. It doesn't really matter, because what we do is, what is the probability that we have to find a design vessel such that the vessels larger than that, they can tear the bridge down, but that with a very small probability. And this design, there may be outliers. Of course, you can have some crane ships or something like that, which will be larger and be more heavy, but they will be so seldom that you should not, that they should not, they would probably not count in your risk analysis.
Right.
So
Well,
that's why we cannot ask for 0 probability, but a small probability.
Understood. So yeah, high risk, high consequence, or very low risk, but high consequence too. So as we saw in Baltimore.
Sure.
Yeah, it's a tough question, and it's not only an engineering question, it's a societal question too.
Yeah,
but
sure.
I would like to thank you very much for this interesting presentation. There's still a few more questions that have not been answered, but those we can get to during the panel discussion later on. So Dr. Pedersen, thank you again. And
thank you for
the presentation. Yes.
Thank you.
Anil, back to you.
Thank you. Thank you, Dr. Pedersen. This was really a great presentation. So moving on to our next speaker, history is very important. And, recently I came to know about Dr. Mercogliano when we had a joint interview with the Daily Mail, and I heard his perspective about what really happens, what was happening in the control room of the Dali ship as they realized they were going to hit the bridge. And that's something very important for we engineers to understand, that when the pilots realize something is happening, what should we do? Dr. Mercogliano has the whole lifetime again in the marine area. He has a bachelor's in marine transportation, master's in maritime history and nautical archaeology, and PhD in military and naval history. He's currently a professor at Campbell University in North Carolina. So I will invite Dr. Mercogliano to give his thoughts on shipping, bridges, and what lies in the future. What can we learn from this incident, from the history, and how do we deal with this as we go in the future? Sal?
Well, good morning. Thank you so much for having me in this presentation. I am not an engineer, so I'm going to caveat my speech with that. I am a former deck officer. I sailed in the Merchant Marine, so I've sailed vessels like Dali. I've actually sailed in and out of Baltimore a few times. My background is, as Anil was talking about, I do kind of the policy side. I also do the history and the security side. I've been running for 3 years now a YouTube channel, What's Going On with Shipping. And the Dali was a subject of great interest on board my channel. Talked about that incident quite a bit, and actually did a video on the incident when it took place that morning that netted quite a few views. But what I want to talk about today is kind of talking about shipping, bridges, and the future. And it's actually going to relate to a lot of the issues that we saw here. Let's see if I get my presentation going here. There we go. So I want to talk about the collision between Dali and the bridge, but I want to put Dali into some context because there were some interesting questions at the very end of the last presentation, which I think is important for us to understand when we start talking about. It takes roughly 3 years to build a ship. It takes, 5 to 7 years to get a bridge up, and then a bridge is there for 50 years. The Francis Scott Key Bridge was built in 1977. Motor vessel Dali was built in 2015. Dali is not a remarkable container ship in any way. She's actually a pretty run-of-the-mill sized vessel for 2024. You're talking about a ship that carries 9,971 TEUs. Those are 20-foot equivalent units. Most of those containers you see on there on Dali are actually 40-footers. They're twice the size of a TEU. But the largest ships, as Anil noted, were roughly 24,000 TEU vessels. Those vessels, I should note, operate on a very set route. The largest container ships operate between Europe and Asia. The biggest ones that come into U.S. ports are limited because of the Panama Canal, the new lane that opened in 2016, to roughly about 16,000 TEU. Dali is 300 meters in length. The massive ultra-large container ships are 400 meters in length, and that is driven by the Suez Canal limitation. You cannot be longer than 399.99 meters to transit the Suez Canal. As you know, the Houthi have diverted nearly all those vessels from going through the Suez Canal. And one of the things we've seen in shipping is when the Suez Canal gets blocked, as it was in 1968 to 75, we see a change in ocean shipping. We saw the introduction of the very large crude carriers and ultra large crude carriers. Does this mean that we could potentially see larger container ships than 24,000 TEUs? I would say we can. They may not be wider, but they may be longer. And so we could potentially see much larger ships. Again, context, I think, is very important. When the Francis Scott Key Bridge was built in 1977, we were shipping around the world at the time about 3 billion tons of cargo. The vast majority of that, over half that cargo, was liquid cargo, largely oil. Today, we ship much different cargo around the world. We've gone from shipping 3 billion tons of cargo in the mid-1970s to last year moving 12 billion tons of cargo. So we move 4 times the amount of cargo by sea today than we've ever done before. And today, tankers are really a minority in the ocean-going fleet. The vast majority of the fleet we see out there are large bulk carriers. Baltimore, in particular, is a large coal port. And so one of the reasons that Baltimore has a 50-foot draft going into the port is because they export a lot of coal out of the region. And of course, container ships have changed that to, again, put Dali into some perspective. Dali carries 10,000 TEU, 10,000 containers. Last month, July of this year, the United States moved through its port 2.5 million TEU. So we move 2.5 million containers in and out of U.S. ports, and Dali represents about 10,000 TEU coming in and out. Ocean shipping around the world has become much more faster and much more volatile. One of the things I talk about a lot is that we've increased not just the volume of traffic, but the velocity of traffic, how fast we move. Dali set sail from the Port of Baltimore at 1 in the morning. She was sailing out through the Chesapeake Bay, and she was embarking on a 35-day voyage southward through the Panama Canal and heading to Sri Lanka. Not an unusual voyage. But she was taking off for a month to head that way. We estimate that based on numbers put together by the UN, there's roughly 100,000 vessels over 100 gross tons. In the most recent report done by Allianz, Allianz is an outfit that does a shipping safety report every year. Based on their numbers for 2022, there were 3,000 major incidences across those 100,000 vessels. Of those, about half of them involve machinery and engine failures of one type or another, very similar to what Dali experienced in her passage out from Baltimore. And since Dali has left, we have seen numerous other failures. We just had a ship leave Baltimore the other day. This was a U.S. Navy vessel. The SS Denebola was leaving, and she suffered a steering failure. We had a very large-scale failure coming out of the Port of New York a few months ago with the APL Qingdao, where the ship lost propulsion. We had a ship coming out of Wilmington, North Carolina, where the propulsion plant dropped and the bulker ran aground off the Cape Fear River. We have seen incidences happen quite a bit recently, and I kind of want to walk you through the Dali incident a little bit to help kind of put some contextualization to what we are talking about here today and the incident. Go ahead, see if I get my video going there. See if I get that moving here. So this is a AIS recording of the events that transpired. I'm going to have this playing in the background. The Dali, again, was a very unremarkable vessel following a very set pattern. One of the things that was noted in Dr. Pedersen's report was the fact that ships sail in and out of these bridges all the time without escort. In the case of motor vessel Dolly, for example, she set sail that morning. She was assisted off the berth by 2 tugboats. There was a docking pilot on board. This is a pilot from the port of Baltimore that was there to assist in the removal of the vessel. And then the ship was under a Chesapeake Bay pilot. The Chesapeake Bay pilot, there's actually 2 on board, were going to assist the ship's master in piloting the vessel out of Baltimore until it cleared the Virginia Capes down in the region of Norfolk and Cape Henry. That morning, the ship had tested all the machinery and equipment as per normal. Everything indicated it was operating fine. I will note a couple of key issues, but since COVID, we've had issues with crew retention and crew replacement. And a lot of crews who are operating on vessels right now are operating without enough leave, without enough training time, and that has become a key issue. This image here shows you the Dolly, and you've probably all seen this multiple times, coming out of the channel. She came off the berth that is directly ahead in this image where the large cranes are, just underneath the chart, about dead center in the bridge is where Dolly came off. And she was proceeding out of the harbor at a set speed of 8 knots, which is typical for ships in the Port of Baltimore. It was standard practice in the Port of Baltimore not to have escorting tugs. You'll notice here, Dolly's gone completely dark at this moment. And what is significant here is that when Dolly goes dark, that's an indication that they have lost power to the main engine and throughout the vessel. What we know from the NTSB, who's released a preliminary report, the National Transportation Safety Board determined that the ship lost power because of the main breakers tripping. The ship's diesel generators, the ship's service diesel generators that provide electricity to the vessel were still running. The ship's main engine was running. But when the ship lost all power, that cut off the main engine, the lube oil, the water feed to the main engine. Dolly had a slow-speed diesel engine with direct drive to the propeller. Once the water and lube oil was cut off, the main engine cut off. And so Dolly right now is under inertia. And having sailed a vessel for many years, I can tell you that the worst sound on board a vessel is no sound whatsoever. The emergency diesel did not kick on within 45 seconds as mandated by requirement. You'll see power coming back on the vessel at this time. They've restored electrical power. At this point, you'll see black smoke emanating from the vessel. This is the 3rd diesel generator coming online. They had 2 of the 4 diesel generators online. The 3rd one is kicked on at this time. You see black smoke emanating from the vessel. The ship is coming at this time abreast of Curtis Bay. Curtis Bay is an ancillary channel. It goes from east to west. And we believe it is that channel that starts to push the Dolly and starts it heading southbound. It's that right turn you start seeing the Dolly make as it begins to turn. The ship's pilot on board, talking with the master, has called for tugs to come back to assist them, and they're preparing to drop the port anchor. We know they dropped the port anchor. You'll see Dolly has lost power a 2nd time now, and that's obviously a key issue. The breakers to the high voltage, low voltage board has tripped multiple times at this point, and they're once again without propulsion. Under emergency power, the ship should have control of their rudder, but it appears that when the ship tripped off the breakers this time, they've lost power again. The emergency diesel comes on. We believe that is the emergency diesel coming back on at this point. That gives them some rudder control, not as much as under main power. It also doesn't give them any propulsion, meaning that the rudder is just using the water that's coming past the vessel. And the ship is beginning its turn to the right here. That's setting it on course for the southern pillar of the Francis Scott Key Bridge. I'll take a step back here and note something. In the United States, harbors are not controlled by any one entity. It's a big flaw in the United States, I would argue. What you see here, the Francis Scott Key Bridge, is under the Department of Transportation for the state of Maryland. The waters are controlled by the U.S. Coast Guard. The channel is dredged by the Army Corps of Engineers. The terminal over there is under the control of the state of Maryland, but leased by private corporations and businesses. And while Baltimore has monthly meetings of all interested parties, it was only the ship's pilots who consistently voiced concern about safety regarding the Francis Scott Key Bridge. For over 10 years, the pilots in the harbor noted the potential of danger should they lose power coming out of this channel and the potential for a bridge strike. Now, everybody knew about bridge strikes going back to 1980 with the Tampa Bay incident. However, the pilots in the Port of Baltimore had raised this concern, and here you see the moment of the strike as they hit and the collapse of the bridge at this moment. The pilot had done everything they could along with the ship's crew to try to get that vessel back into the channel. 30 seconds earlier loss of power, 30 seconds later loss of power, not exactly clear we have the bridge strike of this scale at the time. But this is a problem that we have been seeing. I should note that immediately after this event happened in ports around the United States, there were meetings very similar to those previous meetings in Baltimore where discussions were had about what to do about transiting through channels. In San Diego, for example, which has the Coronado Bridge, very large-scale bridge, and it has a danger of a bridge strike. The Coronado Bridge has the potential to trap half the Pacific Fleet in it. The pilots and the harbor decided to slow passage through the channel and to mandate tugs as they go through the area. What's interesting is one of the reasons Baltimore refused to have tugs escorting ships through is the cost. It would cost additional money. Having a harbor tug with you is about $4,000 to $5,000 an hour additional. It was also limit the number of tugs available to dock vessels. Just before Dali left, another ship, the MSC Toronto, had left. And that would have slowed departures for vessels coming in. Plus, there is another bridge southbound of this, the Bay Bridge, that would require also escorts. And so the problem within Baltimore was if they decided to mandate tugs, that would have slowed entrances and exits of the harbor. It also could have forced cargo to shift to other ports, Norfolk, Philadelphia, New York, New Jersey. And so bridge maintenance and bridge safety has been paramount. We witnessed, for example, the raising of the Bayonne Bridge in the port of New York, New Jersey to accommodate these larger vessels. And Dali, again, is not a red flag in terms of size of vessels. We have much larger vessels than Dali coming in all the time. But what makes Dali very unique here is that Dali had had an incident of a power outage while at the berth. That's being investigated. And there had been warnings throughout the system about this. However, nobody foresaw at least a cataclysmic collapse of the bridge as you witness here. And what we're seeing is safety measures being implemented very slowly in ports, but there is not a federal entity that oversees the harbors that can mandate this. The U.S. Maritime Administration, which is the kind of maritime version of the Federal Aviation Administration, lacks the power, lacks the resources to do this. There is no, for example, vessel traffic system to guide vessels in and out of harbors that are required in U.S. ports. So much like you have air traffic control directing aircraft, you don't have that when it comes to vessels in and out of U.S. harbors. And my fear is that we will see vessels continue to grow in size. I use the analogy from Field of Dreams. If you build it, they will come. Well, as long as there is no provision to stop the growth of vessels, they will keep building them. And the only thing that prevents the growth of vessels is port and harbor limitations or insurance. If it gets too uneconomical to insure a vessel, then you could potentially see a change in the rules. And with that, I'm going to stop right here because I don't want to go past my time. I know you have a very long schedule here, but I'm happy to field any questions that anybody has, and I will be here back for the panel at the end of the conference.
All right. Thank you, Dr. Mercogliano. Sorry if I messed up your name. Very interesting presentation and quite a different perspective than the engineering perspective I think we were kind of used to. There are a number of questions, and I think I would like to start with this one from Marty Roland. It is worded interestingly, so let me read it out. It says, why are shipbuilders so arrogant to think that they can build cargo ships that may not logically pass under certain bridges? Bridges need to be rated for classes of ships. And I know you mentioned that there are legislative issues that are allowing something like this to happen. So I'm curious if you could reformulate your thoughts regarding this question.
Yeah, I think the arrogance has to do with money. I mean, it's a business. And one of the things you get, and one of the reasons when you saw Anil's presentation earlier, and he showed you the size of vessels, you know, for its economy of scale, when the Maersk E-class came out, and then the Maersk Triple E class came out, it was economy of scale. I mean, just, you know, even though I'm not an engineer, I know that if, you know, you increase length, width, and depth, you get a volume cube increase in the size of vessels. And for shippers, that's the key. Understand, you know, go back 50 years ago to container ships. Container ships were a fraction of the size, and the crews were basically 50% to 100% bigger than what you're seeing. Dali coming out had a crew of 22 on board a vessel to carry 10,000 containers. And, you know, if I can be efficient, and what we're seeing right now is there was a massive build of container ships because of the COVID crisis, because there was a big, huge spike in container shipping. Container lines are rich in cash right now. And so they've invested in building vessels, and they're building really 3 types of vessels. They're building those ultra large container ships, those big, huge, massive ones for the Europe to Asia run. They're building ships that can swing between the Suez and the Panama Canal, what are called Neo-Panamax vessels. And then they're building these mid-sized vessels, roughly the size of Dali, a little bit smaller than Dali is what they're building. And, you know, Dr. Pedersen talked about the fact that ships are good for about 20 to 25 years. That's true. But the biggest factor going on in shipping right now is the requirement being imposed on shipping by the IMO for alternative fuel sources. That's an entirely different engineering topic than this today. But one of the things we're seeing is new propulsion methods, hydrogen, ammonia, green methanol, hybrid LNG. A lot of different methods of propulsion are going in. So we're going to see vessels changing in their makeup. But I think, again, if there's no restrictions being set by the ports, by the national entities, they're going to keep pushing the boundaries. The reason that they raised the bridge in Bayonne was because the Port of New York, New Jersey said, we're going to lose out on business because we're not going to be able to accommodate these larger vessels that are coming through the Panama Canal's new lane. And so therefore we have to raise the bridge. It's the same reason that Savannah dredged their harbor, Houston, Charleston, Norfolk, and to a larger extent, Baltimore. Look at the bridge replacement coming in for the Francis Scott Key Bridge. They're making provisions to raise the bridge so that they can accommodate larger vessels.
So, and this is, I'm just rephrasing a question from Alessandro Ponzoni, and I think it also touches on what you brought up in terms of, okay, so if ports are driven by profit and shippers are driven by profit, I think that is not necessarily good for us as citizens. And what can be done about this? Should the U.S. regulate it by having a bureau? What would this bureau look like, and where would it fall under in terms of its governance?
Yeah, unfortunately, in the United States, the waters are controlled by the federal government. Land is controlled by the states and municipal government. So, for example, ports are owned by, Baltimore is a state of Maryland port. Long Beach is a city of Long Beach port. And it's one of the big problems we've had in that we don't have a good coordinating agency to oversee this. One of the big proposals coming forward is to empower an entity like the Maritime Administration to do more port oversight, to do port studies. So that comes in. So for example, when Baltimore decides to bring new container cranes in, is there provisions being put in place? Can the bridge withstand these larger container ships? And, you know, that's something that needs to be done. It is much different than what we see happen in European and Asian nations where ports are national, not really state and local. And, you know, this is one of the reasons why the cleanup effort in Baltimore was a very confusing one, because there were multiple agencies involved at the same time.
I guess there's quite a few more questions as well, but in the interest of time, I'm going to ask one last question. And I'm kind of going to combine two questions from anonymous attendees. So what caused the breakers to trip, and that led to the power outage that caused so much devastation? And the other question I'm kind of going to link to this is, are there records from the shipping companies that we can access as government agencies to know if they're maintaining their ships well enough to pass under our infrastructure?
Yeah, for the first question, the NTSB has that under investigation. We have just received a preliminary investigation from the NTSB that came out, I think it was in June. So we have yet to have the full hearings about this. We don't know what caused the breakers to trip. What we do know is that there was, I mean, the generators were running, the engine was running, but something caused those breakers to trip, and that's what set off the issue here of the loss of power. As Dr. Pedersen talked about, you can restore power. This happens, unfortunately, more often than we think, but it usually happens out at sea where there's not an issue. But in a maneuvering like this, it was a big problem. The second question, I'm sorry, Sherif, what was the second question?
Yeah, so can we require shipping companies to provide their information about their maintenance? I mean, they're passing these huge ships under infrastructure and causing risk to us as citizens of various countries. Can we require them to provide that?
So the good thing is shipping has become safer. One of the initiatives done by the International Maritime Organization, and it's done through a series of memorandums of understandings, is that nations have what's called port state control. Even though, for example, Dali is Singapore flagged with a Indian crew on board, and the company is owned in Singapore, the United States Coast Guard, which is the regulatory body in the United States, has the right to go on board vessels and do inspections to ensure that vessels are meeting the international requirement that is out there. In Europe, it's the Paris MOU. In Asia, it's the Tokyo MOU. But there are agencies that can do it. The problem has to do with the volume. There were 85,000 ship visits in the United States last year, and the U.S. Coast Guard conducted 8,500 inspections. So only about 10% of ships coming in are getting an inspection. And I have to note that the Coast Guard has 11 primary missions. This is probably number 11 in their rank of order. And unfortunately, they don't spend enough on the personnel. This tends to get assigned to junior enlisted and officers who may not have a background in this. They're communicating with crews that don't always speak English very well. And, you know, a lot of the material, a lot of the electronics and engineering aspects of these ships are not uplinked. And so it is very analog. It is very air gapped. So getting some of the information is a problem. And I think one of the issues we do need to do is more robust inspections. Now, I should note real quick is there are third-party agencies that are out there inspecting vessels. These are the classification societies. This is ABS, this is NK, this is Lloyd's. But in many ways, they're having similar problems getting people, having well-trained people doing this. And, you know, if your classification agency is really hard on shipping firms, well, they're just going to go to another classification society. And as if this is not all bad enough, because of the war in Russia, Ukraine, we're seeing the emergence of these new parallel fleet out there, what sometimes are called the shadow fleet, with new classification societies, new registries. And so there's even more danger out there of ships coming into ports that may not be as well maintained and meeting a national standard or an international standard. My apologies.
Okay. Sal, thank you very much for this quite interesting and complex insight into a problem that is not only an engineering one, but a societal and on so many different levels. I look forward to the panel discussion. There's a ton of other questions here, but we are going to perhaps address them in a few hours during the panel discussion.
Well,
So,
I appreciate the opportunity and the diversity of not allowing a non-engineer to come talk to you all.
that is pretty cool. So Sal, thank you again. Anil, back to you.
Thank you, Sal. This was really a unique and a great presentation. We engineers really get to hear about these thoughts, and I think there are a lot there that we can use to develop some kind of warning system, if anything like this happens. So we move on to our next presentation from Dr. Wei Fan from Hunan University of China. His topic is Hunan Provincial Design Standards for Vessel Impact Resistance of Bridges. Dr. Wei Fan, his research has been in the vessel area, vessel pier, ship collision, pier protections, fenders against ship impacts, using new materials. And he has done also extensive amount of work on testing and designing fender systems which can be used to protect the bridges. Incidentally, Dali was not the only accident that happened. Before Dali, a month ago, before a ship, hit a bridge in China, but that was not the pier impact, accident. It was the deck, like Dr. Pedersen talked about, and nearly cut the deck into two parts. Split the deck. So that was one accident. But there was another accident in January of this year in Argentina, where the large ship, hit a bridge, a pier. And in that case, the outcome was different. Nothing happened to the pier bridge. The ship got damaged and got stuck because there was a large pedestal, around the pier, and essentially ship hit the pedestal, got damaged and got stuck there, and it has to be removed from there. So that's a very interesting accident where, the bridge pier didn't collapse, although that ship was 85,000 DWT, and Dali was 116,000. But also, Sal mentioned to me once that Dali was not fully loaded, a lot of containers empty. So the ship in Argentina was also probably as heavy as Dali, but it hit the pedestal, not the pier directly. So with that, some interesting thought came to my mind, and I think we'll be talking more about this. But I'm going to invite Dr. Wei Fan from China to make his presentation, and you might see him under my name, not his name, on the Zoom, because he could not log into the link that we sent him. But it's great to have him. And Dr. Fan, I invite you to make a presentation.
Hello, everyone. Can you hear me?
Yes, please go ahead.
Okay, thank you. First, thank you, Professor Anil Agrawal, for your kind invitation and introducing. It's my pleasure to give a presentation here. My name is Wei Fan, working at Hunan University in China. Today, my presentation is about the Hunan Province Designer Standard for the vessel impact resistance of existing bridges. Sorry, okay. Here is my presentation outline. First, I will introduce some of the ship collision accidents. Second, I will introduce the existing code for vessel impact resistant design of bridge structures, and why we need to make a new design code for existing bridge. Number three, I will talking something about the framework for our new design code. What is different from the existing code? Number four, I will introduce some of the feature in our new design code based on over 15 years work about vessel bridge collisions. Finally, I will summarize my presentation and working experience on vessel bridge creation strategies. Here we can see many photos about vessel bridge creation accident in China. We can find the accident time is here. And most of them caused severe damage or cracked to the bridge. Definitely, we can conclude that in past 2 or 3 years, many terrible vessel bridge accident happened, and safety issue of existing bridge on the vessel creation has becoming increasing prominent. Sorry, whoops.
Dr. Fan, I have a
this
suggestion
year,
to please just click once and wait because I think there's a delay. So when you click again, it just makes the slides move forward or backward. So just
okay.
click and then wait for it.
Okay.
Okay, thank you.
This year, some of the catastrophic accident happened also. In China, the Lixin SARS bridge is scrapped due to the size correction. And in US, the France Scott King Bridge is scrapped. Many people became concerned about the safety of bridge structure on the vessel creations. Oops. When we faced so many vessel bridge creation accidents, we have to thinking something about our design code and what we can do for it. So we began to examine the existing code for creation design. First, we found that many things changed compared to the bridge building times. For example, the channel is upgraded, the ship number increasing hugely, the vessel size became larger and larger. Owing this change, the designed structure capacity of the bridge structure is often insufficient. Second, we found that there is no code for the existing bridge on the vessel creations. This one is China bridge design code, like the ASHTO LRFD in US. Although it has been abrogated several times, it only has a small content about vessel creation issues. It points out the design value of vessel creation action should be determined through the special research. However, it doesn't give any detailed procedure about the special research. In 2020, the Chinese Ministry of Transport has released the specification for creation design of highway bridges. This is China's first specialized specification for creation design. However, the first page of this specification points out the specification is only applicable to new bridge and is not applicable to the existing bridge. The latest specification for maintain of highway bridge only states that the existing bridge should be protected from the vessel creation. However, we don't know how to do it, so we can know that no reasonable standards are available for the evaluation and improving vessel impact resistant performance of existing bridges. In addition, ASHTO and URL code may be available for existing bridge. However, many recent studies point out their limitations. We will talking later. I guess the Professor Couzis will be talking something about this limitation today. Next, I will introduce the framework of our design code. Generally, our design node included 3 steps. The first step is primary assessment. The second step is the detailed evaluations. The third one is improving the design. During the primary assessment, our design code presents the principle and the method for the navigation survey and the bridge survey. After that, we can get the collision's possibility and the collision case. We can define vessel collision's load action and create a bridge analysis model. Best dynamic analysis method, like of the CVIA method and impact force time history analysis method. We can get the bridge response on the required collision events. We can evaluate performance just like safe or unsafe of the existing bridge under the vessel collision based on the capacity demand, capacity to demand ratios. If the capacity is greater than the demand, that means of the low retrofit improvement is required. Otherwise, the impact resistant performance should be improved to attain the expected requirement. Compared to the current codes, the following provisions are first proposed. The first one is point out the various collisions case should be comprehensive considered, like of the typical and complex collision case are clarified, adjust the limitation of the existing standards that focused only on hand-on and applicator collisions. The second one is emphasize the importance of the establish a spectral approximate test for the vessel collision load, overcoming the definition of individual test and is like of the traditional fittings. Number 3 is to define the application range, modeling method, and the analysis principle of different analysis method. Next, I will introduce some new features in our design code. The first one is in our new design code, the level of the vessel collision action is determined by collisions exceeding possibility rather than the feature possibility of the bridge in current code. The vessel collision action is coupled with the post collision failure possibility of the bridge, like the PC is here, and which places some difficulty in determining the vessel impact load. So we found, oops. Sorry, wait a moment.
Yeah, Dr. Fan, there's a lag, I think, with your internet connection. So you just click once and then wait. If you keep clicking on it, it'll just keep going. It'll store it in its memory and keep going.
Maybe some of the network problem is here. So
can we help you go to a particular slide? Scott can help you go to the slide.
the slide, maybe the 15.
Scott, can you help him to go to the slide 15?
Yeah. Oh, yeah, good. Thank you. We can find some limitation of coping the vessel collision action with the failure possibility here. Oops. On the hand, the bridge resistance need to be assumed for each time That means of the iteration required for each times. On the other hand, the equivalent static loads have to be employed in the use of this equation. However, many studies have pointed out used the equivalent static load related to unsafe design result. Okay. Here is my our result. We can find that the limitation use the equivalent static load because the equivalent static method ignore the dynamic effect. The structure demand are significant on the estimate. The result is similarly given that slide of the Professor Couzis teams. I guess the Professor Couzis is talking something more about this. For these reasons, for this reason, we remove the failure possibilities here. We can get the corrections exceeding possibility to these equations. In all the new code, the select exceeding possibility level equivalent that is given in the seismic designs code for consistent risk considerations. We define two different vessel creation actions. V1 actions corresponding to 500 years return period, and V2 actions means of the 200 years return period. And here we can see. The second new feature is about the creation case are not longer limited to the hand-on and applied creations, just like of the site, like of site creations was considered in the new design. And this is a case just like the Taiyangbu Bridge's accident. And this bridge is on the side of the creation. The bridge is cracked. We simulated this side creation accident. It was found that the crack is due to the area in the pier foundation and larger deformation. We compared different creations case. We found that the side creation is the most unfavorable creation case, particularly for a simple supported beams bridge. You can get more detail from this paper. In addition, we examine the rationality of the calendar design code. For example, this is a beam forming case. Our Chinese design code indicated the structure capacity is greater than the demand. That means the bridge is safe. So that means the design code best equivalent static load cannot guarantee the safety of the bridge structure under the side creations. For these reasons, 4 different creations case are specified for the creation design in all the new design code. For each creations case, the analysis method and the modeling method also specified. The third feature is about of the applicable test of the dynamic vessel impact load. We adopt the spectral approximations to assessment validated of the developer budget board forced deformation relationship, overcoming the deficiencies in the individual test and the traditional fits. This is our developer budget board for force deformation relationship. Detailed information can be found in this from these papers. When we When we consider spectral approximations, we found that the developer vessel impact load is more reasonable. When we only examine the applicable of the developer vessel impact loading by limited case by case, the nationality cannot is guaranteed. Additionally, we also refined the performance evaluation, for instance, about of actions combination, impact spectral, impact velocity, and impact locations. We conducted the fragility analysis of the reinforced concrete bridge under the metal hazard effect, just like corrosions combined with the corrosion and scrolling. Best of the cancellation, we found that the structural damage do not always increase of the corrosion energies. On the control, a phenomenon that's like dynamic response decrease with the increase of the impact velocity is observed. Practical impact velocity is involved in the impact vessel impact resistant design. So we don't allow the use of only the maximum impact velocity in all the design code. Several different impact velocity should be considered to obtain the maximum response. So we can find the more detail from these papers. We also found that when a bridge subject to the near-based corrosion, just like the ratio of the impact here to column depth is approximate to 1.5, the performance evaluation should be more caution because the brief shear failure is triggered. For the key bridge, the impact maybe is belong to the near-based corrosions, and the brittle shear failures occur. We also adopt a shear stress calculation formula, which is more suitable for small, like of the shear span ratio. This shear to span ratio is less than 2. Here we can find the result is much gooder is ACE formula. And finally, I will summarize in my presentations. I focus this topic is the 17 years. There are still many issues with the further research. Many factors, just like vessel, bridge, water, and weather, affect the vessel, bridge, corrosion, and consequence. High nonlinears, just like geometry, material, contact, place the extremely difficulty in the analysis and the protection the bridge against the vessel corrosions. We need to do utmost for vessel impact resistant design of bridge structure much more. And this one is this specification that is released in this month, and this is book published in Chinese is maybe 2 years ago. Thank you very much. Looking forward to discussing something about vessel corrosions with you is here and in the future. Thank you.
Thank you, Professor Fan. We have some questions here. We are running just about 5 minutes behind schedule. Remember, we started about 9 minutes late because of some technical issues at the beginning. So we have about 5 minutes for questions. So one of the questions from an anonymous attendee is, I noticed that you removed PC. This is the probability for collapse from the risk equation. I think that makes a lot of sense, but can you elaborate on the reasons you did that? You don't need to go back to the slide, I think. Yeah.
Okay. That means you know, it's PC is means of the consequence. That is the result, just a means of the creation's result.
Yes.
That one is related just like the bridge the resistance. So if you here you typically we use of this one to determine the load. So you determine load, and you need that you needed to determine the structure capacitance here. So that means of the load and the result is coupled together. So if you use of the equivalent static load, that is no problem. But if you use of the dynamic load, that is difficult. So for these reasons, we removing the PC term from the equation.
Okay. A question, this was actually directed to Professor Pedersen. It's on a geotechnical issue that he did not want to respond to because it's not within his area of expertise. But I'd like to ask this of you, and it says, how does the geotechnical, it's written as subsurface characterization modeled in your vessel impact analysis? Like when you did the piles, did you model the subsurface conditions in order to get the pile resistance?
We used of the linears, just like of the model to simulate the pile foundations, pile resistance is here, just like of the fiber-based like element to simulate the pile foundation here. So we can just like use of the like a PY curves to simulate like of the pile and the soil interactions behavior is here.
I see. Okay.
Yeah.
One final question, again, in the interest of time. How do Chinese provisions, this is from an anonymous attendee, how do Chinese provisions compare to the US ones in terms of the level of force?
Sorry, what?
How do Chinese provisions compare to the US ones in terms of the level of force that is applied? Like the demand calculated from Chinese provisions, the force, how do those compare to?
Yeah. I get it.
Yeah.
And then for the just like of the equivalent static load, the Chinese the code the result is similar to US code. It's very similar.
I see.
But here is the difference is between this code Chinese code and the US code. I think is the Chinese code used of the dynamic just like analysis methods here. So the dynamic like of the dynamic impact loading history curve, just like this, just like of the CVIA method that is proposed by Professor Couzis, and all this stuff like simplified dynamic analysis method is include in the Chinese design code. What this is different. In US code, I think there is low like of the dynamic analysis methods here.
I know I said it was the last question, but there was a related question to your response, and this is from Nitesh Sangam. And it says that, of course, like you mentioned, the AASHTO only requires an equivalent static analysis. But can you elaborate on the Chinese requirement for dynamic analysis? Like, how is dynamic analysis considered?
I think today Professor Couzis is topic about of the try to from to the dynamic analysis design from to the dynamic like of the designs here. So I think his presentation we can get more detail about this change.
Okay.
Yeah, I think based on my experience is if you ignore the like of the dynamic effect and the structure, just like the bridge response, is significant on the Alice gate. So if you on the if you the bridge like the response is on the Alice gate, that means if you use the like of equivalent static method is leading to the unsafe design is here.
I see.
So for these reasons, many we can here see lots of the accident happened in past 2-3 years in China. All of this the bridge is designed by the like of the code is here, but the structure, just like the bridge is damaged, is cracked, it's maybe we need to thinking the limitation of the code.
Professor Fan, thank you very much. There are still a number of other questions. These will be shifted to the panel discussion towards the end. Anil, back to you.
Okay.
Thank you very much.
Thank you very much. Yeah.
Thank you, Dr. Fan. It was indeed, very detailed and very interesting presentation. And I think we'll have more discussion about your work during the panel discussion. So moving on, we have the next presenter, Ted Zoli from, he's the National Bridge Chief Engineer at HNTB. Insights from automatic identification system data on vessel collision risk to bridges. I have known Ted almost like more than 10 years. He is one of the most prominent, bridge engineers in the country or around the world. And he's the first structural engineer to receive the prestigious MacArthur Foundation Genius Award. He also received the ENR's Award of Excellence. And he has led the design of numerous innovative first-of-their-kind bridges, such as network arch bridge, gussetless truss, hybrid cable-stayed, or double-curved cable-stayed bridges. Again, his insight is this aspect of looking at the SIP impact on bridges is very important as we look towards dealing with large SIP impacts. So with that, I'll invite Ted to make his presentation.
Thanks, Anil.
Thanks. Start his presentation and hand over in the control.
Yeah, as we're pulling up the slides, I'd just like to say I'm a practicing bridge engineer, and I'm probably the least knowledgeable about the vessel impact side of things of all of this group. But what's important to me to try to get across today, and this is going to seem like a public service announcement for the use of AIS data, I'm very, very much interested in how data can make us smarter about the way we design bridges, and particularly the way we evaluate bridge design, or we reevaluate bridges in the future. So I don't think I have control yet.
Scott?
Yeah, now I do. Yeah, very well. One of the challenges, and I'm sure Mike Knott and others are going to talk about the development of the U.S. codes, and I'm going to speak very specifically about U.S. practice here. But obviously, these codes have been incredible in the sense that they were developed in the beginning in the late 1980s, early 1990s, and have really stood up to the test of time. But an enormous challenge in anything what we do is when we look at how much change happens over time, are we fast enough and capable enough of developing codes that respond to intrinsic changes in the industry? And so I always think about bridge design in this context of we're trying to make the bridge as fit as possible. So I'm the little ant trying to climb the mountain, and the top of the mountain is the best bridge I can design. And the problem is the mountain is moving. And so for me, this question about designing safer bridges against this context of change in the in really a vessel impact and really developing design provisions around that, I get very interested in what is the data telling us. And this other graph on the left suggests that when things change quickly, we need to be innovating more, or maybe we need a shorter development cycle in terms of code. So one of the things that I worry about is if circumstances are changing, is the code development cycle, does it change fast enough? And then we can all imagine, and someone as old as I am has designed bridges 30 or 40 years ago using what was then current technology, and we wonder whether what we designed is still up to the task. So you've heard a lot about this morning already, how much vessels have changed over time, particularly container vessels. And the one statistic, and I'm curious what Sal's perspective on this is, there's really been an explosion of container vessels since 1990s. I use the 1990s as sort of a framework for when we established basic design provisions for vessel impact. And you get the idea. We've at least doubled or tripled the size of vessels. It turns out that vessel speeds have also increased. So we've got if we think about energy, we've got larger, stronger hulls, as Dr. Pedersen mentioned, and we've got faster. So everything is trending in the wrong direction. And just so you thought you were safe, it turns out that also container ship speeds also seem to correlate with, so larger vessels are designed to move faster. And there's also the issue with newer vessels and not just changes in fuel, but changes in efficiency. All of this for the bridge engineer is trending in the wrong direction, right? We've got larger ships. It turns out the larger ships may reduce number of transits, so that would argue for reduced risk. But the size and the speed are really challenging when we think about bridges we've designed in the past and bridges we're either going to replace or design in the future. And so the other piece that I think Dr. Pedersen presented beautifully, but I always worry about, is what is more recent accident data, and do we have accident data sets that we can make sure are relevant in terms of current technologies, right? Obviously, what's changed dramatically since the 1990s, and I'll talk a lot about AIS in a moment here, but we have much better, let's say, backup systems in terms of ship control. We have much better knowledge of where the ship is positionally against other ships. We've got VTS, we've got traffic systems within busy port areas. We have a lot of things that are helping to reduce, let's say, collisions and collision risk. And that's against what I talked about before, the changes in vessel size and speed. This is a reasonable data set and I think we're focused on structural failure. In this case is vessel structure, not bridge structure. So collision and grounding data sets, this idea that more or less half of what we see are crew operational mistakes. And if you go back to Dr. Pedersen's discussion about causal relationships and looking at pilot error, so to speak, I think that gives us lots of insights. But I'm also interested in how these are characterized against vessel type. And obviously, because we're aggregating risk by vessel type, I think finding vessel type specific data is very important in terms of risk assessment, the risk assessment workflows. What I'm really here to talk about is AIS data. And what I want to say to everyone, if you have not looked at AIS, and especially in the US, if you have not looked at AIS data, and we're all going to be in the cycle where we're going to reevaluate bridges we've designed in the past, whether they're safe enough, or bridges we're about to design in the future, that we need as good a data sets as we can. And marine cadastry is about the best data set in the US that there is. And I want to walk you through that data set just so that every practitioner in the US has a clear-eyed sensibility about the quality of this data set and its use in comparison to AASHTO provisions. I'm very interested in data, in how it's changing the practice of bridge design in the US, and the data sets that I'm used to are Wei in motion, how heavy are our trucks, and those data sets have really changed the way I think about how to design bridges, especially in areas where there's a significant proportion of overweight trucks. I also feel the same way about extreme rainfall data. I'm hard at work at looking at these data sets and trying to identify strategies that make bridges safer, and this AIS data set is really robust. So this is a U.S. Coast Guard product. The website, the Marine Cadastry website, or cadastre as the way it should be pronounced. That website, all of this is readily available. Since 2016, you can put a geofence. So if you have a bridge, and in this case, I'm just going to walk you through 3 or 4 bridges where you can put a geofence around the bridge, and every one of those points, and this data set is for about 6 years from 2018 on. Every vessel that has AIS, which is the vast majority of vessels that we're concerned about, as Dr. Pedersen said, anything above 300 gross tons, so anything we're concerned about for large bridges is in that data set. You can see just by the quality of the data set, there's a few points that are, obviously on land. Those are data sets that are not quite correct, but I would say this data is very clean. It needs a little bit of cleaning, but not much. And so what's in this data that's important for bridge designers and at least for me, just to get this out to everyone, that you've got, and the 2 most important pieces are speed over ground and course over ground. So you have both headings and you have speeds. And so again, and then also these are correlated with vessel ID. So you can know the vessel, you can know its speed and know its heading at 1-minute intervals anywhere in the US that has AIS coverage, which is the vast majority. And then you can geofence around a specific bridge. So there's other data that would be useful that's not in that data set, and there's many ways to get at, let's say, deadweight tonnage, something that and I agree with Dr. Pedersen's sensibility. It's not the greatest measure, but that's what's in AASHTO right now. I'm finding deadweight tonnage is not direct from the AIS data set, but you can connect by IMO number or vessel name through, there's a number of resources online to be able to calculate what deadweight tonnage is or any other characteristic. And you can also check the data set from Marine Cadastre against Vessel Finder data sets and see how they compare. Gary Consolazio, as has been mentioned, he's done a lot of work on this front with some of his students. I'm hoping he's done some statewide, for Florida, statewide risk assessments using these data sets. And I hope he just at least has a chance to mention that effort. So what in these, this is all ArcGIS based. So anywhere in the country, anywhere that has coordinates, this gives you both in terms of toolboxes that are within Marine Cadastre. You've got the points. So each point is a location of a vessel, which will have speed and heading, and then you can link the vessel trips. And so this happens to be for the Cape Cod Canal and some bridges that we're looking at. So I thought I'd quickly go through just data sets from bridges that are a wide variety. So FSK was of interest, what Sal had mentioned. Verrazano, obviously a big bridge at the mouth of all of the ports that serve metropolitan New York and really the region. And then quite a small bridge, a bridge in Ocean County in New Jersey, and then the Cape Cod Canal bridges. So these data sets, and you can see here that these data sets are very rich. This is all using a geofence window. So you have all of this data in front of you for really an array of bridge crossings. And then I thought I'd just go through with some of the conclusions, because AASHTO has some, AASHTO design provisions have some very specific aspects, and you can easily test with these data sets whether some of the provisions in AASHTO correlate with actual data. And so On the left here is for Francis Scott Key with these are just deadweight tonnage distributions for vessels of greater than 50 meters. And so if we think about 165,000 deadweight tonnage as it relates to the port of Baltimore, you can see about where the dolly fits in. So a relatively, even though there's a significant number of vessels that are in that size and slightly above it, it's really on the high end. Similarly, if we want to look at, in this case, of speed, and this is transit speed in the vicinity of the bridge, and Sal mentioned that you're around 8 knots, look at how closely that data matches 8 knots. So you clearly have a very regular set of circumstances at FSK, under the Francis Scott Key Bridge, and that just comports. And I can say Sal and I did not coordinate any of our talks beforehand. That's just what the data shows. So the other thing that we can look at in terms of, is just how the classes of vessels compare in terms of speed. And again, because we're aggregating risk on vessel class, I think this data set is that rich. You can go class specific. There's also the question about, is there any monthly variation? And this can be, as I'll mention in a related Chinese study, there can be quite interesting seasonal effects, especially with rivers that have swifter currents. So you can see that, the difference between cargo, passenger, and tanker speeds and so on, and the passenger tends to be on the high end, and the cargo is and bulk is very narrow banded around 8 knots. So we can now look at maybe comparing what we see from that same data set, and if we look at FSK versus Verrazano, we can see that just in terms of speed over ground and knots, you can see much, much higher speeds underneath the Verrazano Narrows Bridge, as you might expect, right? There's not the same proximity of the port itself, and there's less maneuvering. But what's of interest, and I'll speak some later, is that there are speed restrictions, or supposed to be speed restrictions of 10 knots, mostly for North Atlantic right whale safety, and it doesn't seem like those speeds are being very well kept, and regardless of vessel type. The other thing that I would mention is we see very high speeds from cruise ships, and cruise ships are some of the largest ships that we see underneath the Verrazano. So if I were just to overlay, and here all I'm just overlaying is speed over ground distributions for large cargo vessels. So this is only cargo. And if I overlay those two histograms against each other, you see clustering around obviously 8 knots as we've described, but Verrazano's got significantly higher vessel speeds, and that represents its own issue. The other thing that we can look at, and this was a Jason Stith question in the chat, and just to respond to that some, which is, what is the distribution, the statistics on AIS data in terms of distance from center line of channel? And I'm representing this as relative distances. I'll have an LOA representation in a second. But what you can see, and Dr. Pedersen mentioned this, you see this, a bimodal distribution. Ashta would assume a normal distribution, which if you look at the passenger vessels in the right-hand curve, that's closer to normal distribution, but not very well correlated with LOA. The bimodal distribution is because you have ships in alternate directions. So you have more of a normal distribution if you look at directionality. So you can look at and separate upbound versus downbound, or outbound ships, inbound versus outbound ships very easily. And that represents different risk profiles on different components of the bridge. That's easy to capture in this data. And then if we were to look, and one other question is, okay, how much does speed vary depending on where you are in the channel? And again, AASHTO provisions don't really correlate with data sets we see, and these data sets are very different from one facility to another. So I think there's nothing like rich data. And if we were to compare, just generally speaking, that bimodal distribution versus what we would see in terms of just coming up with equivalent normal distribution to try to get this into AASHTO terms from an AIS perspective, and then compare that with AASHTO distribution, which is a function of LOA. You can see that we are, in terms of risk, we're much more conservative using AASHTO distributions than what we see, based on Verrazano in this case, which is a bridge with a very wide navigational channel. So that's one other thing that's important to recognize. This is quite different from FSK. And so just, there's any way you can crunch the data. I'm also very interested in looking at vessel length versus a channel aberration or channel distance, probability of being further away from the channel. And this, for Verrazano, doesn't happen to be well correlated. There's no, the size of the ship doesn't put it so much in the center of the channel. And so this is also, so some of this work that we've done really follows work. And this is, in my view, there's too little of this work yet done in the industry, but there's a very interesting Chinese paper that covers a very complex channel that I don't know how you would design with AIS data. This captures some of what I said about seasonal differences based on just difference in currents and depending on month. Also, this is a bridge with two distinct channels, and you can see the significant differences in distribution, both from AASHTO style distributions, and also, for me, we really have to start thinking if we're, and this is another limitation that, extreme value analysis wasn't really in play in the late 80s and early 90s. Now with the statistics and the capabilities with distributions, I think we can do a lot better job at assessing risk. But just to give you a sense of these channels, you have a sort of upstream and downstream channel. You can think about this as inbound and outbound, and how different those circumstances are with one AIS data set. And this is, if memory serves me, is only for a year or two of data. And so, in my view, you can imagine how you could use this data for a bridge project near you. It gives you so much better sensibilities, and this idea of speed over ground and course over ground gives you a sense of course corrections, accident data sets, where you can look at probability of apparencies. This is just the richest data set out there, and in my view, we can also more carefully investigate the potential for overtaking, as Dr. Pedersen mentioned, this whole bubble, this elliptical bubble around vessels and when they're passing, and looking at how that influences risk. This is some of Gary Consolazio's. Oh, actually, this is not Gary's work. This is work by others who are looking at AIS data more from the perspective of managing the safety of species. And now I'll come back to the speed limitations associated with the North American, or I should say North Atlantic right whale. This is a third party. This is actually NOAA's data set on vessel speed under Verrazano. So you remember we had maybe half of the vessels at over the 10 knots speed limitation, and this is the data set when the speed limitation should be in place, and this is also by vessel class. But you can see that you have significant number of vessels that are over 15 knots. And then you have other third-party outfits that are looking at that AIS data and publishing their own statistics. And you can see the ports of New York and New Jersey, they're roughly half of the vessels are exceeding the 10-knot speed limit. So we can also, we can implement speed limits, but one of the challenges is, are the speed limits, are they being met? Are they enforceable? And so just at the end, just to finish up here, I think the AASHTO methodology has held us in good stead, but these AIS data sets since, especially since 2018 and readily available in the US. Obviously the Chinese studies that I've shown, and there's some good Korean studies on looking at AIS data sets for bridge risk. The AIS data set is a worldwide data set, but the availability of it in the US for US bridges, I think, is exceptional. I really encourage not just the bridge practitioners in the U.S. to look at this AIS data set and make their own evaluations of statistics. But I also encourage really AASHTO to take on and it's a very necessary step to use AIS to make better improvements to look at the AASHTO provisions and hopefully have better representations or even develop workflows where AIS data can be used by designers to have better risk models. And then I really do think that there are some of what we have implicit within AASHTO in terms of curvature, for example, channel curvature or passing density, the channel density and so on. Even tug assists, I think we find that some of the reductions that we take in terms of potential reductions in risk by VTS, by an added pilot, by channel density, these really can be tested against actual data. And 6 years of data pretty well everywhere in the US, I think will give us insights into how to do that better. I've listed in the end the references. What I would suggest to all of you that this AIS data is readily available. I think we all should be using it more and more to give us insights into a better job at assessing vessel risk. Thank you.
Dr. Zoli, thank you very much. This is, again, quite a different perspective on the issue from the previous presentations. There are a number of questions, and I'd like to go back to one that was actually posed to Professor Pedersen, and you had indicated that you also had an interest in responding to this one. It's from Jason Stith, and it goes like this: the probability function f of z spatial distribution for AASHTO uses a length overall as the standard deviation from the normal distribution function. This seems quite conservative. Since you've looked at a lot of AIS data, which you've presented, do you have a recommendation for AASHTO that could be more accurate?
So my recommendation would be twofold in this. One is that I would rely on the AIS data, especially given that there's 5 to 6 years of it in terms of developing a distribution. And then, Jason, the other thing I would say is it's very directional. It's surprisingly directional. And then it varies by class significantly. So the Verrazano data set is an interesting one where let's say the geometry of cruise ships, mostly because of air draft and their need to be under the middle of the bridge to meet air draft requirements, that variability was very different than container ships, for example. So this data set allows you to do, and container ships were very directional where cruise ships were not. So this data set allows you to look at geometric probability directly by class and develop your own distributions. The other piece that I would say is that the use of a normal distribution in extreme value statistics would be unusual. And I think and statisticians better than I need to get engaged in this, but I think we need to look at extreme value analysis to do a better job at predicting the vessel collision risk, and normal distributions is probably too conservative.
Thank you. Second question is from Albrecht Lentz. It goes like this: the AASHTO distribution most likely represents the lateral deviation of ships that have made a navigational error. The actual AIS data you are showing represents the lateral deviation of all ships, most of whom are not making any navigational errors. Could you comment on this?
Yeah, so there are navigational errors in the data set, and I think I can't remember. I think it was Dr. Pedersen that showed grounding circumstances where you had grounding and you had course correction data from AIS. So I think it's exactly what he presented. So the beauty of this data set is it's every ship that transited. Now you could argue that there's nothing like 25 years of data as opposed to 5 or 6 years of data. But I would challenge everyone to think about the data set that we used to develop the AASHTO provisions was really pre-1990s, and so much has changed. even the safety measures, vessel traffic systems, all of these, I think we could test against the geometric probability of aberrancy. And for me, there's nothing like data. I would argue that data gives us better insights. That doesn't mean that data where we have no circumstances where we have aberrant behavior, we have drifting vessels and so on. Maybe that's where extreme value of statistics comes in.
This is from an anonymous attendee. It says, in your initial slides, you show the distribution of causes of accident. Are there data available about the distribution of causes resulting in near misses and violation of sea traffic rules near ports? Like how frequently can you be so close?
Yeah, so that's the Pilates reference that happens to be on this, and so I encourage you to look at that reference set. That's about the best I've seen of most recent accident data sets. There's the challenge of underreported accidents that I think we all recognize. Many bridge engineers, especially in the New York area, have been involved in hit and run, as we sometimes think of them, incidents where they don't necessarily get reported, but there are clearly more accidents than are well represented in databases. But the extreme accidents are there, and I think the data sets are there too. You can infer accidents, and you can look at past tracks, as Sal did in his presentation of FSK. You can use AIS data to go back and look at known accidents and look at vessel tracks in those accidents and derive insights from that. So I think it's all there. It really is. That's the beauty of this data set.
Okay, very interesting. Dr. Zoli, thank you so much.
Thank you.
Anil, back to you.
Thank you. So, thank you, Ted. This was really a great presentation. I agree that AI is using AIS data to, develop risk assessment can be a game changer. So, with that, we have the last presentation from the morning session. Is by large ship collision with bridges, computational modeling and simulation by Dr. Sherif El-Tawil. I am one of the participants in this research. Dr. El-Tawil is Antoine Naman College professor from University of Michigan at Ann Arbor. I and Dr. El-Tawil have been working for last 10 to 12 years, a lot into vehicular impact, ship impact, or related areas, redundancy and robustness of bridges. So this is a work that is in progress, but I think also very interesting. And Dr. Hongfang Wang and Dr. Chen, both my former PhD students, also have contributed this work. So I will invite Dr. Sherif El-Tawil to make his presentation.
Thank you, Anil.
Yeah.
Scott, so thank you. I think I have control. All right, there it is. So this presentation is about large ship collision with bridges, and essentially the word for that is elision. So I could have replaced that sentence with just that word. But I'd like to talk about another different angle in terms of this series of presentations. And the motivation is the collapse, of course, of the Francis Key Bridge. I think that raised our concern worldwide about what is the level of the demand that can be posed by these events. The previous presentations have focused on reducing the risk, but when it happens, like how much force is developed? And that is one of the key objectives that I would like to discuss today. I would like to compare our results to those prescribed by existing codes, specifically the AASHTO, and I would like to also talk about the potential of simulation tools and how those are useful for us as a design community as we design these long span bridges with the risk that is inherent to the shipping around them. So I'd like to talk about here in this slide, the finite element model of a large container ship. This is a Neo-Panamax class ship. It's similar to the Dali. Below are is a comparison between both ships, between the finite element model and the Dali. The Neo-Panamax is typically, in this case, is about 300 meters long. When it's fully loaded, it's about 150,000 tons, and its deadweight tonnage, which is what you can load it with, is about 117,000 tons. The finite element model was created from actual plans for the ship, and validating, as Dr. Pedersen said before, something like this is impossible. Who's going to lend you a ship so that you can crash it and check that it's behaving correctly, your finite element model? And so in simulation, if you can validate small subcomponents, you can reasonably assume that your overall model is going to work well. And so the model in this case contains the sum of the stiffeners, their nonlinear behavior, the contact between all of these various components. These were tested under various pieces of them. We see them working fine. So we have relative confidence in our model. Now, when we started doing this, we said, okay, so how much force can be developed, and how much is a static versus dynamic force? That was a question that was raised before. So we crashed the ship into a rigid pier, and the pier is 5 meters by 5 meters. The initial velocity is 3.5 meters per second. Please excuse me for using kips. A kip is a kilopound, 1,000 pounds. And in this case, the ship had two parts: the bow, which was flared, and the bottom part, which both of them impact the column almost simultaneously. So we track the force that is applied by both parts, and then we add them up together. And I'm showing here a peak force of 51,294 kips. Basically, the result has been filtered with a moving 50 millisecond window. So we've conducted a lot of research on truck impact with bridge piers, and researchers for the past 40 years have been using the 50 millisecond force as a reasonable representation of the impact force that will be generated and used for or considered for design. You could think about other ways of filtering this data, maybe averaging it out or taking over a shorter period. But regardless, you can see that the force is applied over a large period, not a few milliseconds, but the 51,000 is over, like in this case, maybe 0.2 or 0.3 seconds. That is sufficient to cause damage. I see a question here coming. What is the software suite? This is an LS-DYNA simulation. So just a picture showing the crash that is happening, the crushing that occurred, very characteristic. All the various stiffeners are now being crushed on one another. Contact algorithm is allowing this to proceed further with the force that is necessary and occurring. So we thought, okay, well, in the Dali case, the ship was not head-on. It was kind of veered off center. And so we redid our simulation again with the pier shifted about 37 feet away from the center. Basically, the flared bow caught the pier, but also because now it's weaker, it allowed the ship to approach the pier, and basically it started engaging a larger portion of the ship as well. So even though initially the bottom part was not engaged, eventually it caught up, and the force did not drop that much. It dropped, to 46,000 kips. So if you compare this to the existing AASHTO guidelines, so I've put the one on the left are the AASHTO guidelines in US units, and on the right is the calculation that we did. The DWT is 116,000 tons. The speed that was obtained from AIS data at the time is 6.8 knots. It's 3.5 meters per second. The collision force comes to 32,000 kips. The picture below is from a Chinese paper on the relationship between velocity and collision force. And you can see that the AASHTO provisions are in brown over here. You can see that the various provisions compared to it, and you can see that the rigid pier in this case is generating substantially higher forces than the AASHTO provisions and many of the other provisions out there. So that presented an issue for us. Okay, does the rigid pier make sense? Do you think the pier, if it were flexible, would allow the force to decrease? What is the real force that would be applied to a ship in a situation like this? And so we deployed 2 bridges. We had been doing for the past maybe 5 or 6 years research on the robustness of long span bridges. So we have access to multiple bridge models that we had built over multiple years and validated. And so we decided, okay, we're going to take our ship and we're going to crash it into these bridges and see if they will collapse. And if they do not, what is the level of the force that would be generated? So I'm showing here the first bridge that we considered. It is a suspension bridge that was designed based on the 1961 AASHTO specs. It was built and opened to the public by 1968, and that was before the 1990s, early 1990s, when the ship impact provisions came into play. So it was not designed for impact resistance. The central span is 2,100 feet. That's about 700 meters. It is a pretty substantial bridge. It is in existence today, but I'm not at liberty to say which bridge it is. You may recognize it. The towers were 418 feet tall, more than 100 meters, and the model was built in LS-DYNA. And over, like I said, more than a year, we validated the various aspects of the model when we created it. Just to show you the level of detail that went into it, you can see various pictures from different parts of it. So the members of the stiffening truss could buckle, they could yield, and they could fracture. The main cables could also buckle if needed, as well as the suspenders. The various parts of the deck were modeled, including the ability of the deck to yield and fracture, and also crush the concrete as well. And this was important, especially when we were modeling the joints, because we didn't want that to generate large catenary forces, especially when it moved a lot. You can see on the top right, the saddle was also modeled, and we spent a lot of time doing that because you have a terrific force of about 25,000 kips pushing downwards with the friction on the saddle. That makes this almost immovable. But under extreme conditions, when the bridge is about to collapse, you can have the cable sliding over the saddle. So we wanted to model that as well. And on the bottom right, you can see the wind tongue is being modeled in the various aspects of how the bridge is connected to the tower and the cables. And to give you an idea, this is in a situation where we are looking at various suspenders failing and how many it would take to bring down the bridge. And in this case, this was as the bridge was collapsing and the tower and its various components were failing. Another bridge that we've been working on is a cable-stayed bridge. This is an even bigger one than the previous bridge that I mentioned. The central span is 1,500 feet. The tower is pretty substantial and much thicker than the steel one for the previous bridge. And again, this bridge had a lot of details that were modeled, but I'm not going to go into it just in the interest of time. But I wanted to show you again kind of the limitations of the modeling technique we're using. This is the bridge when various cables were failed, and this is how it would basically behave as it's collapsing. But again, I'm not going to present results related to the cable-stayed bridge. This is something we're currently working on. I'm just going to present results with respect to the suspension bridge itself. So we have here the ship. You remember the model that I described a little while ago. It's now approaching the bridge pier, and it is a steel bridge pier in this case, 150,000 ton ship, and approaching at 3.5 meters per second or 6.8 knots. So I'll play the video as you know, you can watch as I talk. Basically, both parts of the ship are approaching the pier. They're now pushing against it. And if the demand is too high, the pier is going to buckle under the extreme forces and the rest of the bridge would follow. But in this case, this did not happen. The bridge had sufficient robustness and strength to prevent this from occurring. And if you look at the force distribution, the force time history, and look at the displacement time history, you can see that the pier deformed about 4 feet, that's 1.3 meters. And interestingly, there was enough elasticity that it pushed the ship back again. These are massive structural components. And in this case, the peak force, which I believe would be a design force, given how long the force acted, it acted for about half of a second, as you can see up there, was 42,000 kips. So substantially higher than the 32,000 kips that we would estimate from the AASHTO provisions. But again, we'll discuss this towards the end. Looking at the pier, you can see that the impact location is the height of the ship. Again, this is a massive bridge with a massive ship impacting it. They kind of do not dwarf one another as you would expect. And if I zoom in on the pier zone, you can see that the plastic rotation that occurred is 0.06 radians. 0.06 radians within the unified facilities criteria for blast, for example, and even for seismic criteria is something that is survivable. This member would have been deleted if it had reached our fracture criteria. It was not. But the reason I'm talking about the 0.06 radians here is because it is reasonable for a steel component to be able to achieve this. But anyway, moving forward, we thought, okay, in the Dali situation, the ship was off-centered, so let us do that here. What if the ship caught only the flared part of the bow and basically allowed it to kind of move in a little bit? So it looks like this was a more severe impact. The displacement was higher. It reached 6 feet, about 2 meters. Again, the rebound, you could sort of see some of that. And the peak force is about the same in this particular case. I'd like to mention that the ship model does not include solid fluid interaction, as there's a question here from Arjang about this. And so you could think that perhaps this is not an underestimation of what is happening. But again, these are some very preliminary simulations that we have been doing over the past month or so. Looking at the damage that has occurred, you can see that the Dali ship, and again, this is not proof that the simulation is perfect. It is just showing that we are able to model with substantial reasonableness, if that is a word, the kind of damage that is occurring at the deck level and below as well. We then said, okay, we have the model working, we have the ship model operating perfectly as well. Well, what if we came in at an angle? How would that change things? So we tried to model an oblique impact, and basically the ship is coming in at 45 degrees. Now, the behavior of the bridge is quite different when you push it along its axis versus pushing it perpendicular to its axis. Perpendicular to the axis, you are mobilizing the frame, and the frame is a massive steel structure. Perpendicular to the axis is different than parallel to the axis. When it's parallel to the axis, you're starting to push on a cantilever that is 400 feet tall, 130 meters tall, and supported at the very top with the cables. But like I mentioned, the cable it goes over the saddle. The force is about 25,000 kips with a large coefficient of friction there holding it in place. So we weren't really sure what would happen in a situation like this. And so the bridge approached, the ship approached the bridge, whacked into it, and basically, again, stopped. The rebound happened, and the impact force was about 41,000 kips or so. So in this particular case, the bridge survived this impact. So I'd like to summarize where we are, and I have a couple more slides before I wrap up. So the demand that we calculated exceeded that computed from the AASHTO equation. For the off-center impact, we reached 43,000 kips versus the estimated 32,000. That's a 35% increase. Okay, that could be within the range of variability of the equations that were developed. But for the oblique impact, the recommendation is to use half of the force in the direction parallel to the bridge axis. And in this case, the component was 29,000 kips, which is from the previous slide, 40,000 kips at 45 degrees. And that is an 80% increase, more than the AASHTO provisions. Multiple speakers today talked about the force level or force demands from the AASHTO provisions being perhaps insufficient. And I think this is more evidence of that here. I should also mention that when the force is applied to the bridge has now moved 4 or 5 feet. You have a terrific P delta effect, a question from Jordan Warnicki here, that could lead to the buckling of these massive components. But in this case, that did not happen. In all of the simulation cases for this large Neo-Panamax class ship, the tower was damaged. It sustained significant plastic deformations. but those deformations were deemed acceptable for the steel components that were used. Certainly, this is something that would need to be ascertained in the future, but this particular bridge would have survived an impact that was similar to the Dali ship crashing into the Baltimore Bridge. Now, going forward, I just, again, have a couple more slides. As a structural engineer and thinking about these issues, I wanted to bring up two terms that we've talked about a lot in a previous workshop that we organized, Anil and I, a couple of years ago. I guess it's 4 years ago now. That one, like this one, was attended by hundreds of people as well. And we debated the terms redundancy and robustness. So redundancy is the ability of a bridge to perform its function in a damaged state. That's one definition. Another is that for it to have the ability to divert the forces to an alternate load path. And all of these stem from concepts that we took as students in terms of a bridge that, or a structure that is determinate or not determinate. If it's determinate, then it can have multiple load paths. The AASHTO provisions are based heavily on the concept of redundancy. Now, robustness is another very important capability of a bridge, and it's the ability to withstand adverse conditions. Okay, that's a definition, I think, in this particular case that's not very precise. But that's it. That's the whole idea. We don't know what those adverse conditions are. So it's the ability to withstand issues that the bridge was not designed for. We like to see robustness in our buildings, and that's a topic that Anil and I, again, worked on in the past. How would you feel about living in a house of cards where you lose one column and the entire bridge collapses? So robustness is a very necessary condition for bridges, but the AASHTO provisions does not have a single reference to robustness. In contrast, the Eurocode talks about robustness quite a bit, but it doesn't talk about redundancy. And to many people, these two terms are interchangeable, but in reality, they're not, because you can see situations where one is present and one is not. Now, for coming back to the topic of this bridge, redundancy is generally not possible because these massive bridges are typically based on a frame like the one I'm showing on the right there that has two members. Sometimes there's just one large member. And if you lose one of those two members or you lose that last member, you do not have redundancy. What you have is robustness, and it is the last line of defense. There is no way around that. And interestingly, robustness is not a design consideration at present, and I strongly argue that it should be. So my thesis and that of my co-authors is that robustness must be ensured in long-span bridges. So what is the design ship? And this was debated quite a bit by our previous authors. There will always be a bigger ship. The 33,000 gross weight tonnage ship that collapsed the Sunshine Skyway is 1/5 the weight of the Francis Key Bridge Dali that caused that bridge to collapse. And it's probably going to be 1/5 of a bridge 50 years from now. What is the design ship? How do we ensure robustness? And the other thing that was also debated was, okay, who is responsible? And we learned from Sal that this is a really complex question for limiting the size of the ships that go into these ports. The ports are motivated by profits, as the shipping companies. That is something as designers, I did not know personally before today. And so I would think that the design philosophy that kind of makes sense from a structural engineering perspective is to employ a multi-layered approach. We should have a minimum lateral resistance for piers. And that should not be a small number. This should be a huge number that would force a designer to make these bridge piers significant. We should also deploy supplementary protective systems such as barriers, raised platforms, whatever, dolphins that would prevent direct impact between a ship and a bridge. And these should not be arbitrary systems. They should be designed using a performance-based approach that has been very successful for seismic and for blast situations. These should be designed no damage for low-level impact. We don't want to go repair these every 2 weeks, but in a severe situation, they might fail. They might allow the ship to pierce the defense, but the bridge will not collapse. The collapse is so severe and it affects so many people and it affects the economy in such a strong way that this should not be even something that we should entertain. And I believe that simulation has the ability to allow us to ascertain this performance and develop meaningful acceptance criteria. Srini, I know I'm almost done. Okay? So the software that is available now for simulation is quite well established. I'm showing here some of our previous research on truck impacting roadside hardware. You can see that in this situation, even larger truck impacting a bridge pier, the comparison between the various components is actually pretty good for these cases. So in conclusion, long span bridges do have inherent robustness. That's because they're so big, but is it enough? We've shown that a suspension bridge built in 1962 does have sufficient robustness to withstand the Dali. Our preliminary simulations with the cable-stayed bridge, I didn't show that, also survived direct impact, but the key bridge did not survive. It had a different type of structural system. We think that a multi-layered approach needs to be implemented. Piers must have a minimum lateral resistance. We cannot imply that this could be low. It has to be very large. Direct impact should be prevented using a system within a performance-based design framework. This performance is something that would be set by engineers as they think about what is acceptable. And we offered a kind of framework for that based on concepts from earthquake engineering. And simulation is a reliable means for achieving this. And we're currently looking with our models right now at how these large ships would collapse from the impact situations. So Srini, all yours. Thank you.
Thank you, Sherif. I know you self-moderated some of the questions. Nice presentation. There are a couple more questions. Two of them are more related to geotechnical aspects of it. Did you consider soil structure interaction, soil in LS simulations? And how did you model your foundation aspects of it?
In this particular case, we did not model the, so these were done quite quickly, actually. We did not model the soil structure interaction part of things, nor the fluid structure interaction. These models were available to us from our previous work, and what we did was we just crashed the ship into them. There are fluid structure interaction components that are pretty substantial. So as the ship moves, it is moving with a lot of fluid and water around it, and that will increase the impact force, perhaps substantially. And that would make the AASHTO provisions even less conservative than what I mentioned. And the soil structure interaction may change the behavior at the boundary, but the impact was pretty high in both of these bridges, and I'm not sure that it would be substantial, but it's something that we are working on right now.
There's a question from anonymous attendee. Did the truss structure of the FSK bridge increase the overall damage?
Can you say the question again, Srini, please?
Did the truss structure of the FSK bridge increase the overall damage?
Oh, no, I don't think so. I think the FSK bridge collapsed because the piers were so thin. So it had an A structure. If I were building this again, I would not have an A structure of two thin components. I would have a large pier instead of two parts. So that is it. The two legs, one of them fails, the bridge is going to collapse. It's a very simple situation, unfortunately.
Srini, I just wanted to add something that I've been thinking about. When you look at the truss bridges and suspension bridges and cable-stayed bridges, suspension-based towers and cable-stayed based towers, they're under a lot of compression, and that significant amount of compression itself gives rise to a stronger section. The truss bridge at the top, it's essentially sitting on the bearing, and it's almost like for the impact force, it's cantilevered. So, yes, that factor is there in the collapse. But again, what exactly led to the collapse, what are the mechanism that has to be investigated by using a similar kind of crash technology. Unfortunately, the FSK bridge drawings are not available right now, but when we get it, then we'll like to look at that. So you can continue with the next question.
Another question, sorry, from Syed Lahari. I believe the ship anchor was dropped before hitting the pier. Was this accounted for in your model?
It wasn't. We used the 6.8 knots based on the AIS data that we had available to us. So this was the best estimate of the approach speed that we had. I know that these ships are so heavy that the anchor might take several miles for it to become effective. But again, ship behavior and dynamics is not my area of expertise, so I am not sure.
Another question from an anonymous attendee. Where did you calculate the load from the rigid pier part of the model?
So the force was obtained from the contact relationships for both parts. So we created two parts, one for the upper part of the flared bow and the bottom one was for the bottom bow, and we added them together.
One last question is from Chengwen Lu. How sensitive the impact force would be in terms of bridge column stiffness?
It appears that it is not that sensitive because when it impacted the rigid pier, we had about 51,000 kips. When it impacted the bridges, again, for these massive bridges, the piers are quite stiff. It dropped from 51,000 to 40 to 45,000. So looks like it's maybe a 20% effect, but it was actually smaller than I thought it would be.
Second part of this question is what are your thoughts on using energy-based approach versus force-based approach on bridge column design?
I think that energy-based approaches require certain assumptions that are a little bit hard to rely on. I would always kind of base these on force-based. That's my opinion as a structural engineer who's done this for a while. I think, of course, energy-based approaches have always worked in various other fields. But in this particular case, I would prefer a force-based approach.
There's one interesting question from Alessandro Panzon, which probably we can also take into later in the panel too. Do you think that a preventive retrofitting of the triangular frame of Baltimore pier support could have saved the bridge?
If we had
preventive retrofitting.
Can you say that again? If we had
a preventive retrofitting of the triangular frame of Baltimore pier support.
Do you think if we could have removed the triangular frame? Is that what you?
No, retrofitting the triangular. Retrofit.
All right, I lost you there, Srini. I don't know what
Sreenivas means it's
yeah.
Retrofit or repair of the triangular portion of the pier.
Oh, the retrofit.
Mm-hmm.
Actually, I mean, I don't want to speculate because I don't have the actual dimensions of the pier. If I were to guess, and it's purely a guess, I would say not. I think in a case like that, it would have been best to prevent the bridge from reaching the pier at all. The bridge, again, you have to keep in mind, it was never designed for the impact. It was built well before the provisions came into play. And so it was never intended to do that. So I don't know if that answers the question, but it's certainly something for the panel discussion.
Thank you, Sherif. There are a couple of other questions. Probably you can take them to panel discussion. And
sure.
Thank you.
Look forward to that.
You and your co-authors, co-presenters.
Yes, thank you, Sharif, and thank you, Srini, and all the panel members. I think it's 12:30. That's what the time we are planning. So also it's time for the lunch break. I will request all the attendees to leave your login as it is because it will make it very difficult for us to evaluate the PDH hours. We have to actually estimate the time you are in the meeting room. So please leave as it is. We break for the lunch right now, and panelists also please leave your computer as it is. You can just mute, and we meet promptly back at 1 o'clock when we'll have 3 more presentations. One by Gary Consolagio, then McElnott and David Taylor from New Zealand. And then we'll have the panel discussion before we close the symposium. But it has gone very well. We are right on time, and it has been very, very interesting discussion, a lot of interesting thoughts, future ideas. So it's great. And let's take a break. We meet at 1 o'clock. Thank you.